Earth's history is written in catastrophe. From gamma-ray bursts to asteroid impacts and supervolcanoes, this video explores cosmic and planetary disasters that nearly wiped out life and asks which one could happen again. If you love this kind of content, you're in the right place. Imagine a morning 66 million years ago. The sun rises over what will one day be called North America, casting golden light across a landscape that would seem alien to human eyes. A triceratops lifts her massive head from drinking at a river. Her 3 horns glint in the early light. She has no way of knowing that this is the last morning of her kind. The sky is clear. Birds that are not quite birds flutter between trees that are not quite the trees we know. Somewhere in the distance, a Tyrannosaurus Rex calls out, claiming territory. Life is everywhere. Life is thriving. Life has ruled this planet for over 300 million years, and there is no reason to think it will ever end. But high above, invisible and silent, something is falling toward Earth. It has been falling for millions of years, crossing the vast emptiness of space. It is 6 miles wide, made of rock and metal, and it is moving at 40,000 miles per hour. In the next few seconds, everything is about to change. The Triceratops sees a flash brighter than 1,000 suns, and then the screen goes black. Cut to the present day. We see the same landscape, but now it is covered in grass and modern trees. Cars drive past on a highway. People go about their lives completely unaware that they are walking on a graveyard. Beneath their feet lie the bones of giants, the remnants of an entire world that was erased in an instant. This is our planet, Earth. From space it looks peaceful, a blue marble floating in the darkness. But that peaceful appearance is deeply misleading. Our planet is under constant assault from the universe around it. The sky above us is not empty. It is filled with threats we cannot see, moving at speeds we cannot imagine, carrying energy we cannot comprehend. 5 times in Earth's history, nearly everything died. Not just some species, not just animals in one region. Almost everything, everywhere, all at once. Scientists call these events mass extinctions, but that clinical term does not capture the true horror of what happened. These were moments when the planet became a tomb, when the very air turned toxic, when the oceans filled with poison, when the sun itself disappeared behind clouds of ash and dust. And here is what should keep you awake at night. The forces that caused those extinctions are still out there. Asteroids still orbit the sun. Volcanoes still simmer beneath our feet. Gamma rays still shoot across the galaxy. The universe has not stopped trying to kill us. We have simply been lucky so far. But how long does luck last? Chapter 1. The Invisible Threat. Let us begin with the most terrifying threat of all. The one we would never see coming. The one that could end everything before we even knew it had started. Somewhere in our galaxy, right now at this very moment, a massive star is dying. It is not dying peacefully. Stars do not go gentle into that good night. This star is collapsing, its core imploding under its own impossible weight. In the final seconds of its life, all of the matter at its center compresses into a space smaller than a city. The temperature rises to billions of degrees, and then, in a fraction of a second, something happens that releases more energy than our sun will produce in its entire lifetime. This is called a gamma-ray burst. Imagine taking all the light and energy from 100 billion stars and focusing it into a beam narrower than a pencil. Then imagine that beam shooting across space at the speed of light, piercing through anything in its path. This is not science fiction. This is real. This happens somewhere in the universe roughly once per day. Now, here is the terrifying part. Light travels at 186,000 miles per second. Nothing in the universe moves faster. When a gamma-ray burst is aimed at Earth, we would not see it coming. There would be no warning, no alarm, no time to prepare. The first moment we knew about it would be the moment it struck us. What would happen? The burst would hit the side of Earth facing it. In seconds, it would strip away half of our ozone layer. The ozone layer is an invisible shield in our atmosphere that protects us from the sun's deadly ultraviolet radiation. Without it, the sun becomes a weapon. Every living thing on the surface would be exposed to radiation levels that cause cancer, destroy DNA, and kill cells. But it gets worse. The gamma rays would also trigger chemical reactions in our atmosphere, creating nitrogen dioxide. This reddish-brown gas would block sunlight, triggering a sudden ice age. Temperatures would plummet. Plants would die. The food chain would collapse. And all of this would happen in days, not years. Sound impossible? Sound like something from a disaster movie. Then let me tell you about something that happened 450 million years ago. Scientists call it the Ordovician extinction. At that time, Earth looked nothing like it does today. There was no life on land yet. Everything lived in the oceans, and the oceans were thriving, filled with bizarre creatures we can barely imagine. Trilobites scuttled across the seafloor. Nautiloids, some as long as school buses, hunted through the water. Life was everywhere, diverse and abundant. And then, without warning, 85% of all ocean species vanished. Not gradually, over millions of years. Not through competition or slow environmental change. They disappeared in what geologists call a blink of an eye. When we examine the rocks from this time period, we see something shocking. We see evidence that the ozone layer was destroyed. We see chemical signatures that match exactly what we would expect from a gamma-ray burst. Something in space killed nearly everything in the oceans. We do not know where the burst came from. We do not know which star exploded. That star is long gone now, its remains scattered across the galaxy. But the evidence of its death is written in Earth's rocks, in the sudden absence of fossils, in the empty layers where life should be, but is not. Today, astronomers have identified several stars within striking distance of Earth that could produce gamma-ray bursts. The closest is about 8,000 light-years away. That might sound far, but in cosmic terms, it is next door. If that star were to explode today and aim its death beam at us, we would not know about it for 8,000 years. The light from the explosion would take that long to reach us. But here is the nightmare. That star might have already exploded 7,999 years ago, and the gamma rays could be racing toward us right now, just 1 year away from striking Earth. We would have no warning. We could not stop it. We could not shield ourselves from it. The first sign would be a bright flash in the sky, and then half the planet would be bathed in lethal radiation. Every GPS satellite would fry. Every computer in orbit would go dead. The power grid would surge and fail. And that would just be the beginning. But here is what you need to understand. As terrifying as gamma-ray bursts are, as apocalyptic as their effects would be, they are not even the deadliest thing that has hit our planet. That honor belongs to something much more familiar, something we can actually see coming, something that has killed more times than we can count. Chapter 2. Reading the Rocks. There are people who can read Earth's history like you and I read books. They are called paleontologists, and they do not need words or recordings or photographs. They need only rocks. Every layer of stone beneath our feet is a page in Earth's diary, written over billions of years. And when you learn to read those pages, you discover something absolutely chilling. Meet the scientists who first decoded this story. In the late 20th century, geologists around the world began comparing notes. They were studying rocks from different continents, different time periods, different environments. And they noticed something disturbing. At certain points in history, the fossils just stopped. Imagine you are reading a book filled with names and stories. Page after page describes hundreds of different characters, all living their lives, all interacting with each other. And then you turn the page, and 90% of those names are gone, simply erased. No explanation, no warning, just absence. This is what the rocks show us. And it does not happen just once. It happens 5 times in Earth's history. 5 moments when the Book of Life had most of its pages ripped out. Let me show you how scientists discovered this. We need to understand the timeline. Earth is 4.5 billion years old. To put that number in perspective, if we compressed all of Earth's history into a single year, with January 1st being the planet's birth and December 31st being today, then the dinosaurs would not appear until mid-December. Human beings would show up in the last minute of December 31st. All of recorded human history, every empire and war and invention would happen in the last second. On this timeline, the 5 mass extinctions stand out like scars. Dark moments when the planet nearly became sterile. The first mass extinction happened 450 million years ago. We have already discussed this one. The Ordovician extinction. Something, possibly a gamma-ray burst, killed 85% of ocean species. The second happened 375 million years ago. The Devonian extinction. This one unfolded in waves over millions of years, but the result was the same. 75% of species vanished. The evidence points to toxic oceans, poisoned by volcanic eruptions and suffocated by lack of oxygen. The third happened 252 million years ago, and we will come back to this one because it is the worst of all. Scientists call it the Great Dying. 96% of ocean species died, 70% of land species gone. Life came within a whisper of ending completely. The fourth was 200 million years ago. The Triassic extinction. Massive volcanic eruptions split continents apart, filled the atmosphere with carbon dioxide and cooked the planet. 80% of species disappeared. And the fifth, the most famous, happened 66 million years ago. The dinosaurs. We will spend considerable time with this one because we know exactly what killed them. We found the murder weapon. But first, you need to understand how scientists figured this out. How do you prove that something killed nearly everything millions of years before humans even existed? You look for clues in the rocks. One scientist, a geologist named Walter Alvarez, was studying rocks in Italy in the late 1970s. He was looking at layers of limestone that had formed at the end of the age of dinosaurs, and he noticed something strange. Between the layer containing dinosaur fossils and the layer above it, there was a thin band of clay, just a few centimeters thick. Above this clay layer, the dinosaur fossils vanished, gone. Not just dinosaurs, but ammonites, marine reptiles, many types of plankton, all gone. Walter brought samples of this clay back to his father, Luis Alvarez, who was a Nobel Prize-winning physicist. Together, they analyzed the chemistry of this mysterious clay layer. And they found something that changed our understanding of Earth's history forever. The clay contained enormous amounts of an element called iridium. Now, iridium is extremely rare on Earth's surface. It sank into Earth's core billions of years ago when our planet was still molten. You might find a few parts per billion in normal rocks. But in this clay layer, the iridium levels were 30 times higher than normal. Where does iridium come from? Space. Asteroids and comets contain far more iridium than Earth's crust. When Luis Alvarez saw these measurements, he realized what he was looking at. This thin layer of clay was not clay at all. It was dust, the pulverized remains of an asteroid, and it was found in rocks all over the world at exactly the same time period. Something from space had hit Earth so hard that it vaporized, spreading a layer of dust around the entire planet. The hypothesis was revolutionary. Most scientists at the time believed dinosaurs went extinct gradually, perhaps due to climate change or disease. The Alvarez team was suggesting something far more catastrophic. They were saying an asteroid struck Earth with such force that it caused a mass extinction in a matter of years, not millions of years. The scientific community was skeptical. Many people did not believe it. They demanded proof. They wanted to know if an asteroid hit Earth, where is the crater? That question launched a search that would take a decade to solve. Scientists began looking for a crater that was the right age, the right size, and in the right location. It had to be big. An asteroid capable of causing a worldwide extinction would create a crater at least 100 miles across. And it had to be 66 million years old, matching the age of the iridium layer. They searched and searched. They found craters in Africa, in Europe, in Australia. But none of them matched. They were either too old, too young, or too small. Some scientists began to doubt the hypothesis. Maybe there was no crater. Maybe the asteroid hit in the ocean and left no trace. And then, in 1990, they found it. Not on land, not by accident. They found it by studying gravity. A company searching for oil deposits in Mexico had created detailed gravity maps of the seafloor in the Gulf of Mexico. And these maps showed something incredible. Buried beneath 1/2 mile of sediment, hidden underwater and invisible from the surface, was a ring, a perfect circular structure 110 miles across. They named it Chi after a nearby town. Drilling confirmed it. The rocks at the crater's edge were 66 million years old. They contained shocked quartz, a type of crystal that only forms under the pressure of a massive impact. They contained melted rock that had been turned to glass in an instant. This was it, the smoking gun, the place where the dinosaurs died. But finding the crater was just the beginning. Now scientists wanted to know exactly what happened on that day 66 million years ago. They wanted to reconstruct the disaster moment by moment, and what they discovered is more terrifying than any disaster movie. Chapter 3. The list of suspects. Before we dive into the details of how the dinosaurs died, we need to step back and see the bigger picture. We need to understand all the ways the universe can kill a planet. Because what killed the dinosaurs is just one item on a very long and very frightening list. Think of Earth as a small boat floating in a violent ocean. That ocean is space, and it is not empty. It is filled with objects moving at incredible speeds, colliding with each other, exploding, releasing energy that could vaporize planets. Our little boat has survived for 4.5 billion years, but it has been hit many times. And it will be hit again. Let us catalogue the threats from space first. Asteroids are the most obvious. These are chunks of rock and metal left over from the formation of the solar system. Most of them orbit peacefully in a belt between Mars and Jupiter, millions of miles away. But their orbits are not stable. Gravity from Jupiter and other planets nudges them. Over millions of years, some of them get pushed into orbits that cross Earth's path. There are thousands of these near-Earth objects, and we have only found about 40% of them. The others are out there right now, invisible, some of them on collision courses with our planet. Then there are comets. Think of these as dirty snowballs made of ice and rock that orbit the Sun in huge elliptical paths. Some comets take thousands of years to complete one orbit. They spend most of their time in the outer solar system, far beyond Pluto, in a region so dark and cold that we can barely detect them. But every so often, something disturbs their orbit. Maybe two comets collide. Maybe a passing star's gravity tugs on them, and suddenly they fall inward, accelerating toward the Sun, accelerating toward US. Comets are even more dangerous than asteroids because they move faster. They can hit Earth at speeds of 150,000 miles per hour. We have already discussed gamma-ray bursts. These are the long-range killers, death beams shot across the galaxy by dying stars. Then there are supernovas, which are similar but less focused. When a star explodes, it releases a blast wave of radiation and energy that can sterilize every planet within 50 light years. There are dozens of stars in our cosmic neighborhood that could go supernova at any time. Solar storms are another threat. Our sun is not calm. It is constantly exploding, sending out flares and coronal mass ejections. Usually these storms are weak, causing beautiful auroras when they hit Earth's magnetic field. But every few centuries, the sun produces a storm so powerful it could destroy our entire technological civilization. In 1859, a massive solar storm called the Carrington Event hit Earth. It was so powerful that telegraph wires sparked and caught fire. Auroras were visible as far south as the Caribbean. If that storm hit today, it would fry every satellite in orbit, destroy transformers in power grids, and send us back to the pre-electric age in a matter of hours. Now let us talk about threats from Earth itself. Beneath our feet, the planet is restless. The solid ground we walk on is just a thin crust floating on an ocean of molten rock. Sometimes that molten rock finds a way to the surface, and when it does, it can kill millions. Supervolcanoes are volcanic systems so large they make regular volcanoes look like firecrackers. When a supervolcano erupts, it does not just form a mountain. It collapses, creating a crater called a caldera that can be 50 miles across. The eruption ejects thousands of cubic miles of rock and ash into the atmosphere, enough to bury entire countries and block out the sun for years. There are at least 20 known supervolcanoes on Earth right now. One of them sits beneath Yellowstone National Park in the United States. Tourists go there every year to take pictures of geysers and hot springs, completely unaware that they are standing on top of a chamber of molten rock 55 miles long. This volcano has erupted 3 times in the last 2 million years. The last eruption was 640,000 years ago. When it blew, it covered half of North America in ash. Trees were buried under 10 feet of volcanic debris as far away as Iowa. And that was a small eruption compared to what that system is capable of. Then there are the slow killers. These are the threats that do not strike like lightning, but strangle like a python, taking their time, making the planet uninhabitable, degree by degree. Climate change is one of these. When too much carbon dioxide enters the atmosphere, it acts like a blanket, trapping heat. Temperatures rise, ice melts, ocean currents change, weather patterns shift, and if the warming goes too far, it can trigger feedback loops that make the heating unstoppable. More heat means less ice. Less ice means less sunlight reflected back to space. More sunlight absorbed means more heat. Around and around it goes, accelerating until the oceans themselves begin to boil away their oxygen. This brings us to ocean anoxic events. Anoxic means without oxygen. When oceans warm up, they lose their ability to hold dissolved oxygen. The creatures living in the water begin to suffocate, but it gets worse. When oxygen disappears, certain bacteria thrive. These bacteria produce hydrogen sulfide, which is basically the same poison gas used in chemical weapons. The gas bubbles up from the ocean depths, turns the water purple and green, and eventually escapes into the atmosphere, making the air itself toxic. Sound like science fiction? This has happened multiple times in Earth's history. We have found the evidence in rocks, purple and green layers where ocean sediments should be red or brown, chemical signatures of hydrogen sulfide, and most tellingly, the sudden absence of everything that lives in oxygen. Now here is the truly frightening thing. All of these threats are connected. They can trigger each other. An asteroid impact can trigger volcanic eruptions on the opposite side of the planet. Volcanic eruptions can cause climate change. Climate change can cause ocean anoxic events. Ocean anoxic events can release greenhouse gases that cause more climate change. Once you push the Earth's climate past a certain point, it can start falling, like a boulder rolling down a hill, gathering speed impossible to stop. Scientists have calculated the odds of these various disasters. The chances of a civilization-ending asteroid strike in any given century are roughly 1 in 5,000. Not great odds, but not terrible. The chances of a supervolcano eruption in the next century are about 1 in 700. Solar storms powerful enough to destroy our technology happen roughly once every 500 years. We are overdue for one. But here is what keeps scientists awake at night. We are constantly monitoring for these threats now. We have telescopes watching for asteroids. We have satellites measuring volcanic activity. We have sensors monitoring the sun. And what we have discovered is chilling. In 2013, an asteroid exploded over Russia. It was only 60 feet across, smaller than a house. But when it detonated in the atmosphere, it released energy equivalent to 30 atomic bombs. The shockwave shattered windows across an entire city. More than 1,500 people were injured by flying glass. And here is the terrifying part. We never saw it coming. No telescope detected it. No warning was issued. It came out of the direction of the sun, which meant our telescopes were blind to it. The first anyone knew about it was when the sky lit up and the explosion shattered their windows. If that asteroid had been just slightly larger, if it had struck a city directly instead of exploding high in the atmosphere, it could have killed millions. And we would have had zero warning. This is our reality. We live in a cosmic shooting gallery. Objects are constantly whizzing past us at speeds that would vaporize cities. Some we see, most we do not. And the big ones, the ones that could end civilization, the ones that could make humans go the way of the dinosaurs, those are still out there, orbiting invisibly in the darkness, waiting for gravity to pull them into our path. But there is one killer we know more about than all the others, one that we have studied in exquisite detail, one where we found the crime scene, identified the murder weapon, and reconstructed exactly what happened. This killer struck 66 million years ago, and what it did was so catastrophic, so absolute in its destruction, that it changed the course of life on Earth forever. Chapter 4. The Smoking Gun. Let us go back to that morning 66 million years ago. The day the world ended. We need to understand not just what happened, but how it happened, moment by moment, because the details are what make this story truly horrifying. The asteroid that killed the dinosaurs was approximately 6 miles wide. To put that in perspective, that is the distance from downtown Manhattan to Central Park and back. Imagine an object that size, made of solid rock and metal, falling from space. It had been falling for millions of years, drifting through the solar system, tugged by the gravity of planets, slowly spiraling inward toward the sun. It probably originated in the asteroid belt between Mars and Jupiter. Something, perhaps a collision with another asteroid, knocked it out of its stable orbit, and gravity did the rest, pulling it slowly but inevitably toward the inner solar system, toward Earth. The asteroid did not suddenly appear. It was not aimed at us deliberately. The universe is not malicious. It is simply indifferent. This chunk of rock just happened to be in the wrong place at the wrong time, as was Earth. Two objects on intersecting paths, both following the laws of physics, both obeying the pull of gravity. The collision was inevitable from the moment their orbits intersected. As the asteroid entered Earth's atmosphere, it was traveling at 12 miles per second. Let me help you understand how fast that is. A bullet from a rifle travels at roughly half a mile per second. This asteroid was moving 24 times faster than a bullet. At that speed, air does not have time to move out of the way. The asteroid compressed the atmosphere in front of it, heating it to temperatures hotter than the surface of the sun. The air itself became a plasma, glowing white-hot. The asteroid took less than 1 second to cross through the entire atmosphere. It did not slow down. Air resistance is meaningless at these speeds. And then it hit. The impact site was in shallow ocean water off the coast of what is now the Yucatan Peninsula in Mexico. The asteroid punched through the water as if it was not even there. It hit the seafloor and kept going, drilling down into the Earth's crust like a bullet through paper. In the first microseconds after impact, the asteroid vaporized. Not melted, vaporized, turned instantly into gas from the sheer force of the collision. The rock of the seafloor vaporized too. Billions of tons of material converted to plasma in a fraction of a second. The energy released was unimaginable. Scientists estimate it was equivalent to 10 billion atomic bombs, the kind dropped on Hiroshima, all exploding at once. To give you another comparison, take every nuclear weapon that exists on Earth today, all 13,000 of them, and detonate them simultaneously. The asteroid impact was 700 times more powerful than that. The explosion created a crater 110 miles wide and 12 miles deep in less than a minute. The Earth's crust did not just crack, it liquefied. Rock behaved like water, splashing up in waves hundreds of miles high. The impact was so violent that it created an earthquake measuring 11 on the Richter scale. Every earthquake in recorded human history has been less than 9.5. This was an earthquake that shook the entire planet. Seismic waves rippled outward through the Earth's crust at speeds of 5 miles per second. When these waves reached the other side of the planet, they converged, focusing all their energy on one point. The ground rose and fell like ocean waves. In India, where the shock waves converged most strongly, massive volcanic eruptions were triggered. Lava began pouring out of the ground, starting eruptions that would continue for thousands of years. But the earthquake was just the beginning. The asteroid hit in shallow ocean, which meant that billions of tons of water were instantly vaporized and displaced. This created tsunamis. Not the kind of tsunamis we see today, where waves might be 30 or 40 feet high. These were walls of water over a mile tall. They radiated outward from the impact site at the speed of a jet aircraft, traveling at 500 miles per hour. When these mega tsunamis hit the coasts of North America, they traveled hundreds of miles inland, erasing everything. Forests were ripped out of the ground. Mountains of sediment were torn up and carried inland. We have found these deposits in places like Texas and Alabama, thousands of feet above current sea level. The water carried fish, plants, pieces of the asteroid itself, and mixed them all together in a chaotic jumble. When the water receded, it left behind layers of debris that we can still see today in rock formations. These are the graves of everything that lived near the coasts on that day. But we are only a few minutes into the catastrophe. The worst is still to come. The impact ejected material with such force that it achieved escape velocity. Millions of tons of vaporized rock, melted debris and asteroid fragments were thrown upward at speeds exceeding 7 miles per second. This material shot out of Earth's atmosphere into space. Some of it went into orbit, some of it escaped Earth's gravity entirely and flew off into the solar system, where it probably still drifts today. But what goes up must come down. Within hours of the impact, this material began to fall back to Earth. Not in one place, everywhere. The debris spread out in a ring around the planet, and then it all fell at once, re-entering the atmosphere at hypersonic speeds. Imagine millions of meteors, all entering the atmosphere simultaneously, all over the world. The friction from re-entry heated them until they glowed red-hot. The sky turned into a broiler. The entire atmosphere became an oven. Forests on every continent spontaneously burst into flame. The heat was so intense that even creatures hiding in burrows underground could feel it. Everything on the surface, everything that could not find shelter, everything that could not get underwater or deep underground, burned. We have found evidence of this global firestorm in rocks all over the world. Layers of soot, the remains of burned vegetation at exactly the right time period. The fires consumed forests on every continent. The smoke rose into the atmosphere, billions of tons of it, joining the dust and debris already there. And then came the darkness. The combination of asteroid dust, vaporized rock, and smoke from the global fires created a cloud that encircled the entire planet. This was not like volcanic ash from a normal eruption. This was thicker, darker, and covered more area. The particles were so fine they stayed suspended in the atmosphere for months, potentially years. The sun was completely blocked out. At noon on a clear day, it would have been as dark as the darkest night. No sunlight reached the surface. Without sunlight, temperatures plummeted. Remember, this is a planet that had been warm and tropical. Dinosaurs had lived near the poles. There was no ice at either the North or South Pole. The average temperature was much higher than today. But within weeks of the impact, temperatures dropped by 50 degrees. The planet went from a greenhouse to an icebox in the time it takes to change seasons. Plants cannot survive without sunlight. They need it for photosynthesis, the process that converts light energy into chemical energy. Without light, plants began to die. First the leaves, then the whole plant. Forests that had survived the initial firestorm now withered and died in the cold and darkness. Plankton in the oceans, the tiny plants that form the base of the entire marine food web, died by the trillions. When the plants died, the herbivores began to starve. Triceratops, hadrosaurs, sauropods, all the giant plant-eaters that had ruled the land for millions of years, had nothing to eat. They could not migrate to find food because there was no food. The whole planet was dying. These animals, some of them weighing as much as 10 elephants, began to starve. Imagine the desperation. Imagine these magnificent creatures wandering through dead forests, searching for anything green, finding nothing but ash and darkness. The herbivores died within months, and when they died, the carnivores lost their food source. Tyrannosaurus rex, the apex predator, the most fearsome hunter that had ever lived, began to starve. At first, they could feed on the corpses of dead herbivores, but those ran out. Some carnivores probably turned to cannibalism, hunting their own kind. But it was not enough. There was simply not enough food to sustain them. The cold was relentless. Dinosaurs, despite what old movies showed us, were probably warm-blooded, or at least partially so. But they were large. Large animals need huge amounts of food to maintain their body temperature. In the freezing darkness of the impact winter, with no food available, they could not generate enough heat. They froze and starved simultaneously. The impact also triggered acid rain. When the asteroid vaporized rock, it released sulfur and nitrogen into the atmosphere. These combined with water vapor to create sulfuric acid and nitric acid. The rain that fell was as acidic as battery acid in some places. It burned the leaves of any plants that had somehow survived. It poisoned rivers and lakes. It leached into the soil, making it toxic. The extinction did not happen instantly. It unfolded over months and years. Different species died at different times. The large herbivores went first, starving when the plants died. The large carnivores followed soon after. Creatures that lived in the ocean suffered too. The plankton died, which meant the fish that ate plankton died, which meant the larger fish died, which meant the marine reptiles died. By some estimates, 75% of all species on Earth went extinct. Not just dinosaurs. Birds, mammals, reptiles, amphibians, fish, invertebrates, plants. An entire world was erased. Ecosystems that had been stable for tens of millions of years collapsed. But some things survived. Small mammals, about the size of rats, that could hide in burrows and hibernate through the worst of the impact winter. Crocodiles and turtles, which could go months without eating and could survive in murky, oxygen-poor water. Some birds, particularly the ancestors of modern waterfowl, which could eat seeds and aquatic plants, and many insects, which had short generation times and could survive in small refugees. These survivors inherited a dead world. When the dust finally settled, when the sun finally broke through the clouds after months or years of darkness, when temperatures began to stabilize, what remained was a planet covered in ash. Dead forests, empty oceans, silence where there had once been the calls of thousands of species. But life, as it always does, found a way to continue. The survivors began to multiply. Without the dinosaurs dominating every ecosystem, mammals had a chance to evolve and diversify. Over millions of years, they grew larger, filled the empty niches, and eventually became the dominant form of life on land. One of those mammal lineages eventually led to primates, and one of those primate lineages eventually led to us. Humans exist because an asteroid killed the dinosaurs. If that rock had missed Earth, if it had passed by just a few hours earlier or later, the dinosaurs might still rule the planet. Mammals might still be small, shrew-like creatures hiding in the shadows. There would be no humans, no civilization, no one to look back and reconstruct what happened. The asteroid that killed the dinosaurs was a disaster beyond comprehension, but it was not the worst extinction event in Earth's history. That distinction belongs to an event so catastrophic, so absolute in its destruction, that scientists struggle to understand how life survived at all. Chapter 5. The Year Without Summer. Before we discuss the worst extinction, we need to understand just how devastating the asteroid impact was to the climate. We need to see how blocking out the sun affects every single living thing on the planet. And the best way to understand this is to look at what happens when humans accidentally do something similar. In April of 1815, a volcano called Mount Tambora in Indonesia erupted with a violence that stunned the world. It was the largest volcanic eruption in recorded human history. The mountain literally exploded, ejecting so much material that it lowered its own height by 4,000 feet. Ash and sulfur dioxide shot into the stratosphere, spreading around the globe on high-altitude winds. The sulfur dioxide created a haze that reflected sunlight back into space. Not as bad as the asteroid, not even close, but enough to cause global effects. The following year, 1816, became known as the Year Without Summer. Snow fell in New England in June. Crops failed across Europe. Famine spread. In Switzerland, Mary Shelley spent a cold, dark summer indoors and wrote a novel about a scientist who creates a monster. That novel was Frankenstein, and it exists because a volcano blocked out the sun. Now imagine that effect magnified 1,000 times. That is what the asteroid impact did. The darkness lasted not for one summer, but for months, possibly years. And unlike humans who could store food and wear clothes, the dinosaurs had no protection. Let me walk you through what happens to an ecosystem when the sun disappears. We need to start at the bottom of the food chain with plants. Every plant on Earth gets its energy from sunlight through photosynthesis. Inside every green leaf are structures called chloroplasts. These are like tiny solar panels. They capture photons of light and use that energy to convert carbon dioxide and water into sugar. This sugar is the fuel that powers the plant. It is also the foundation of nearly all life on Earth. When the sunlight stops, photosynthesis stops. The plant can survive for a while on stored energy, but within days or weeks those stores run out. The leaves wither. The plant stops growing. If the darkness continues, the plant dies. Not just individual plants, not just certain species. Everything green dies. Forests, grasslands, floating plankton in the ocean, all of it. Now think about what eats plants. Everything. Insects, fish, dinosaurs, mammals, all of them depend on plants, either directly or indirectly. When the plants die, the herbivores start starving within weeks. A triceratops weighing several tons needs to eat hundreds of pounds of vegetation every single day just to survive. When that food disappears, the animal begins to digest its own fat reserves, then its own muscle, then it dies. The carnivores survive a bit longer because they can eat the dying herbivores. But this is temporary. Imagine you are a Tyrannosaurus rex. At first, there are corpses everywhere. Easy meals. But those run out quickly because nothing new is being born. The herbivores are all dead or dying. No young are being raised. The supply of prey dwindles day by day. Soon you are alone, one of the last predators on a dying planet, with nothing left to hunt. Some carnivores probably turned to scavenging. They ate rotten meat, diseased carcasses, anything they could find. Others turned on each other. But this only delays the inevitable. Without plants producing new energy from sunlight, without herbivores converting that plant energy into meat, the entire food chain collapses from the bottom up. The ocean ecosystems failed just as completely. In the oceans, photosynthesis happens in tiny floating organisms called phytoplankton. These microscopic plants drift near the surface where sunlight penetrates the water. They are so small you cannot see them individually, but they exist in such enormous numbers that they produce more oxygen than all the forests on land combined. Every other breath you take comes from phytoplankton. These organisms die within days of losing sunlight. They simply stop producing energy and sink to the bottom. When they die, everything that eats them begins to starve. Small fish and krill that feed on plankton die next. Larger fish that eat those small fish follow. And at the top of the marine food web, creatures like mosasaurs, giant marine reptiles the size of buses, found themselves in an empty ocean with nothing to hunt. The cold was another killer working alongside starvation. When temperatures dropped 50 degrees in a matter of weeks, many animals simply could not adapt fast enough. Reptiles are particularly vulnerable to temperature change. Their body temperature depends on their environment. When it gets cold, they become sluggish. Their metabolism slows. They cannot move quickly. They cannot hunt. They cannot escape predators. Even if a dinosaur found food, its body might not be able to digest it properly. Digestion requires energy and specific body temperatures. A cold dinosaur is a dying dinosaur. Some species probably tried to migrate toward the equator where it might be warmer. But remember, this was a global catastrophe. There was nowhere warm to go. The entire planet was freezing simultaneously. Now, let me tell you about one of the most heartbreaking discoveries in paleontology. In North Dakota, scientists have found a fossil site called Tanis. This site appears to preserve creatures that died on the very day of the asteroid impact. They have found fish with impact debris in their gills. They have found animals buried in positions that suggest they were hit by the initial shockwave. These are the last photographs of the dinosaur age, frozen in rock, showing us the final moments before everything changed. Among these fossils, they have found dinosaur bones. Not adult bones, juvenile bones. Young dinosaurs that had just hatched or were still growing. They never got a chance to live. They died within hours of the impact, buried by tsunamis and debris flows. Looking at these fossils is like looking at photographs from Pompeii. We see individual tragedies preserved in stone. We see the end written in fossilized bone. But some creatures survived, and understanding why they survived teaches us important lessons about extinction. The survivors shared certain characteristics. They were small. Small animals need less food than large ones. A mammal the size of a rat might only need a few seeds per day to survive. A Tyrannosaurus needs hundreds of pounds of meat. The survivors could also hide. Mammals lived in burrows underground where they were protected from the initial firestorm and the extreme temperature swings. Underground, the temperature stays relatively constant. It does not matter if the surface is freezing. A few feet below ground, it stays tolerable. Many survivors were also omnivores. They could eat anything. Seeds, insects, dead animals, roots, whatever was available. Herbivores that could only eat fresh plants died. Carnivores that could only eat fresh meat died. But creatures that could scavenge, that could eat varied diets, that could make do with whatever they found, those creatures survived. Crocodiles and alligators survived, and scientists think it is because they can go months without eating. They have extremely slow metabolisms. A crocodile can eat one large meal and then fast for half a year. During the impact winter, while dinosaurs starved, crocodiles simply went into a state of near hibernation and waited it out. Turtles survived for similar reasons. They can also fast for long periods. Many turtle species can also survive in very low oxygen water. When the oceans became oxygen poor and toxic, most fish died. But turtles, which can hold their breath for hours and can even absorb some oxygen through their skin, managed to persist. Some birds survived, which is remarkable because birds are actually dinosaurs. They are the direct descendants of small theropod dinosaurs. The birds that made it through were probably species that lived near water and ate seeds, fish and insects. These food sources were more available than fresh vegetation. Seeds in particular can remain viable for years in the soil. While adult plants died, their seeds survived underground, waiting for better conditions. After the dust settled, after the sun finally returned, after temperatures began to normalize, the world that emerged was empty. Imagine walking across an entire continent and seeing no large animals, no herds of anything, no predators, just small creatures, insects, and the stubborn plants that sprouted from buried seeds. The recovery took millions of years. This is hard for humans to grasp because our lives are so short. But imagine trying to rebuild all the diversity of life, all the complex ecosystems, all the intricate relationships between species, starting almost from scratch. It is like burning down a library that took centuries to build and then rewriting every book from memory. The first forests to return were dominated by ferns. We know this because we find thick layers of fern spores in the rock record right after the extinction. Ferns are pioneer species. They grow quickly in disturbed environments. They probably covered the dead landscape in a carpet of green. But it would take thousands of years for trees to return and millions of years for complex forests. Mammals began to diversify rapidly. With the dinosaurs gone, ecological niches were empty. There were no large herbivores grazing the plains, no large predators stalking prey. Mammals, which had spent 150 million years as small, nocturnal, shrew-like creatures, suddenly had opportunity. Over the next 10 million years, they evolved into hundreds of new forms. Some became grazers, some became predators, some grew large, some stayed small but became highly specialized. Eventually, one lineage of mammals took to the trees and evolved better vision, grasping hands and larger brains. These were the primates. And 55 million years after the asteroid impact, the first primates that could be called human ancestors appeared. Another 65 million years of evolution led to US. This is the legacy of the asteroid: death and rebirth, catastrophe and opportunity. The dinosaurs ruled for 150 million years, and then they were gone in an instant. Mammals, the underdogs, inherited the Earth. If you could travel back in time and move that asteroid just slightly so it missed Earth, everything would be different. Dinosaurs might still dominate. Mammals might still be rat-sized. You and I would not exist. But as devastating as the asteroid impact was, as total as its destruction seemed, it was not the worst extinction in Earth's history. That honor, that terrible distinction, belongs to an event that happened 186 million years before the dinosaurs died. An event so catastrophic that it nearly ended all complex life on Earth. An event that makes the asteroid impact look merciful by comparison. Scientists call it the Great Dying. But that name does not capture the true horror of what happened. A better name would be the Great Suffocation or the Great Poisoning, because that is exactly what occurred. Chapter 6. The Great Dying. 252 million years ago, Earth looked alien. If you could visit this time period, you would not recognize the continents. All the land on Earth was joined together in one massive supercontinent called Pangaea. Pangaea means all Earth in ancient Greek, and it was literally all the land merged into one vast landmass, surrounded by a single enormous ocean called Panthalassa. Standing in the middle of Pangaea, you would be thousands of miles from the nearest ocean. The interior of the continent was a brutal desert, one of the driest places that has ever existed on Earth. Temperatures could swing from scorching heat during the day to bitter cold at night. Life clung to the coasts and the few river systems that snaked through the interior. But despite the harsh conditions, life was thriving. This was the end of the Permian period, and Earth was home to some of the strangest creatures that ever lived. There were gorgonopsids, saber-toothed predators that looked like a cross between a lion and a reptile. There were parasaurs, massive herbivores covered in bony armor. In the oceans swam trilobites, ancient arthropods that had existed for nearly 300 million years. On land grew vast forests of seed ferns and conifers. This was not the age of dinosaurs yet. Dinosaurs would not evolve for another 20 million years. This was the age of synapsids, the ancestors of mammals. For over 50 million years, these creatures had dominated the land. Life had found a way to adapt to Pangaea's harsh conditions. Ecosystems were stable, biodiversity was high. There was no reason to think anything was about to change. And then something went catastrophically wrong. In what is now Siberia in northern Russia, the ground began to crack open. This was not a normal volcanic eruption. This was something on a scale that defies imagination. An area the size of Western Europe began to erupt. Not one volcano, not 10 volcanoes. The entire region became a hellscape of volcanic vents, each one pouring out lava. These eruptions were not explosive like Mount St. Helens. They were effusive, which means the lava simply flowed out of the ground like water from a broken pipe. But the sheer volume was staggering. Over the course of 1 million years, these eruptions released enough lava to bury the entire United States under 1,500 feet of molten rock. The lava flows in Siberia were so massive that in some places they are 3 miles thick. But the lava itself was not the main killer. The real danger came from the gases released by the eruptions. As magma rises through the Earth's crust, it brings with it dissolved gases. Carbon dioxide, sulfur dioxide, methane, hydrogen chloride, all of them bubbling out of the molten rock like carbonation from a shaken soda. In a normal eruption, these gases are released and then dispersed. But these were not normal eruptions. They lasted for 1 million years, continuously pumping gases into the atmosphere day after day, year after year, century after century. The carbon dioxide was the first problem. Remember, carbon dioxide is a greenhouse gas. It traps heat in the atmosphere like a blanket. As more and more carbon dioxide was released, global temperatures began to rise. Not quickly, not overnight, but steadily, relentlessly, degree by degree, over thousands of years. The planet began to cook. Scientists estimate that global average temperatures rose by 18 degrees. That might not sound like much, but remember, this is an average. Some regions, particularly near the equator, became as hot as 130 degrees. The interior of Pangaea, already a desert, became uninhabitable. Nothing could survive there. Creatures tried to migrate toward the poles, toward cooler regions, but there was a limit to how far they could go. The poles were only slightly cooler, and they were already crowded with displaced species competing for dwindling resources. The heat caused droughts. Rivers dried up. Lakes evaporated. Plants that had adapted to Permian conditions could not adapt fast enough to the changing climate. Forests began to die. Grasslands turned to deserts. The plant die-off triggered a cascade of extinctions as herbivores lost their food sources and carnivores lost their prey. But the worst was yet to come. The heating affected the oceans in ways that turned them into death traps. Warm water holds less dissolved oxygen than cold water. This is simple chemistry. As the oceans warmed, they lost their ability to hold oxygen. The surface waters stayed relatively oxygenated because they were in contact with the atmosphere. But the deep ocean, the abyss, began to run out of oxygen entirely. When deep ocean water loses its oxygen, certain bacteria thrive. These are anaerobic bacteria, meaning they do not need oxygen to survive. In fact, they prefer environments without oxygen. These bacteria process sulfur instead of oxygen, and as a byproduct, they produce hydrogen sulfide. This is the same chemical that gives rotten eggs their smell. But in large concentrations, it is deadly poison. Hydrogen sulfide prevents cells from using oxygen. Even if you breathe pure oxygen, if there is hydrogen sulfide in your blood, you will suffocate from the inside. As these bacteria multiplied in the deep ocean, they began producing massive amounts of hydrogen sulfide. The gas accumulated in the depths, turning the water purple and green. This was not a small area. This was happening in oceans worldwide. And then, slowly, the poisoned water began to rise. Ocean currents normally circulate water between the surface and the depths, bringing oxygen down and nutrients up. But as the surface water warmed, this circulation stopped. The boundary between oxygenated surface water and toxic deep water rose higher and higher. Eventually, the poisoned water reached the surface. We have found evidence of this in rocks around the world, layers of purple and green sediment that should not exist, chemical signatures that can only come from hydrogen sulfide, and most tellingly, the sudden extinction of nearly everything that lived in the ocean. Trilobites, those hardy survivors that had endured for 300 million years through multiple extinction events, vanished. 96% of all marine species went extinct. Not just rare species, not just vulnerable species, almost everything. Coral reefs disappeared, fish populations collapsed. The oceans became graveyards. But the horror did not stop at the water's edge. Hydrogen sulfide is a gas. It bubbles out of water just like carbon dioxide bubbles out of soda. As the oceans released this poison gas, it began to accumulate in the atmosphere. Coastal regions became toxic. Animals breathing the air near the ocean were poisoned. Plants along coastlines wilted and died. The atmospheric hydrogen sulfide had another deadly effect. It destroyed the ozone layer. Remember from our discussion of gamma-ray bursts, the ozone layer protects Earth from the sun's ultraviolet radiation. Without it, the sun becomes a weapon. As the ozone layer thinned, ultraviolet radiation levels spiked. Any creature exposed to direct sunlight suffered radiation burns. DNA damage skyrocketed. Mutation rates increased. Cancer rates soared. On land, 70% of species went extinct. The great forests collapsed. The synapsids that had ruled for millions of years nearly disappeared. Only a few species survived in isolated refuges, small populations clinging to life in the few places that remained tolerable. The extinction unfolded in pulses. There were multiple waves of dying spread across hundreds of thousands of years. Just when life seemed to stabilize, conditions would worsen again and another wave of extinctions would hit. Some scientists think there were as many as 3 distinct pulses, each triggered by intensifying volcanic activity in Siberia. The most disturbing thing about the Great Dying is how slowly it happened compared to the asteroid. The asteroid killed in years. The Great Dying killed over hundreds of thousands of years. It was a slow strangulation, a gradual poisoning, a steady march toward oblivion. Species watch their world become unlivable degree by degree, year by year, generation by generation. There was no sudden catastrophe, no single moment when everything ended. Just a relentless grinding decline into a planet-wide nightmare. At the peak of the extinction, Earth was a hellscape. The oceans were toxic, the atmosphere was poisonous, the land was scorched by heat and bathed in deadly radiation. 96% of ocean life was gone. 70% of land life was gone. Complex ecosystems built over millions of years had collapsed. Earth had nearly become sterile. And here is what should terrify you. We are releasing carbon dioxide into the atmosphere today at a rate comparable to the Siberian eruptions. Not as fast, not yet, but close. We are warming the planet. We are acidifying the oceans. We are seeing oxygen dead zones expand in coastal waters. The mechanisms that cause the Great Dying are active right now. We are conducting a planetary experiment that has been run before, and we know how it ended. The difference is that the Siberian eruptions were natural. Nobody could have stopped them. But our emissions are a choice. We have the technology to stop. We have the knowledge of what happens if we do not. The question is whether we will act before we trigger the same feedback loops that nearly killed everything 252 million years ago. Chapter 7. Death from the Deep. Let us dive deeper into the nightmare of ocean anoxic events, because this is one of the most likely threats we face today. Understanding how oceans die is crucial to understanding our current crisis. Imagine the ocean as a living organism. It breathes, it circulates oxygen, it supports life at every depth from the sunlit surface to the crushing darkness of the abyss. But this breathing depends on a delicate balance. When that balance tips, the ocean can transform from a cradle of life to a chamber of death in a geological eye blink. Let me explain how a healthy ocean works. At the surface, sunlight penetrates the water. Phytoplankton use this light for photosynthesis, producing oxygen as a byproduct. This oxygen dissolves into the water. Meanwhile, cold water at the poles sinks because cold water is denser than warm water. This cold, oxygen-rich water flows along the ocean floor toward the equator in massive currents called thermohullin circulation. Think of it as the ocean's bloodstream, carrying oxygen to the depths. At the same time, warm surface water flows from the equator toward the poles to replace the cold water that sank. This creates a global conveyor belt, a circulation system that has run for millions of years. Nutrients from the deep ocean are brought to the surface. Oxygen from the surface is carried to the depths. Life thrives at all levels. The system is in equilibrium, but this system can break. When the planet warms too much, several things happen simultaneously. First, the surface waters warm up. Warmer water is less dense than cold water, which means it does not want to sink. The circulation begins to slow. Less cold water sinks at the poles. Less oxygen is carried to the depths. Second, warmer water holds less dissolved oxygen. This is basic chemistry. Heat makes oxygen molecules more likely to escape from water into the air. As temperatures rise, the water at the surface loses oxygen-carrying capacity, even as it continues producing oxygen through photosynthesis. Third, the boundary between warm surface water and cold deep water becomes sharper. In a healthy ocean, there is gradual mixing between layers. But in a warming ocean, the warm layer sits on top like oil on water, refusing to mix with the cold layer below. This boundary is called a thermocline, and when it strengthens, it acts like a barrier, preventing oxygen from reaching the depths. The deep ocean begins to run out of oxygen, slowly at first. Fish and crustaceans that live in the depths begin to suffocate. They try to move upward into oxygen-rich water, but there is limited space there, and competition is fierce. Most of them die. As oxygen levels drop below a critical threshold, anaerobic bacteria take over. These bacteria flourish in low oxygen conditions. They metabolize sulfur compounds and release hydrogen sulfide. The concentration of this poison gas increases day by day, year by year. The deep water turns purple and green, the color of dissolved sulfide. Now, here is where it becomes truly catastrophic. The poisoned water does not stay in the depths. Ocean currents continue to flow even when circulation is weakened. Deep water is pushed up along continental shelves. Underwater earthquakes and landslides can disturb the layers. Storms can mix surface and deep water, and slowly, inexorably, the boundary between safe water and toxic water begins to rise. When the hydrogen sulfide reaches the surface, it comes in contact with the oxygen. The two chemicals react violently, consuming the oxygen and producing sulfur compounds that make the water acidic. This creates a deadly positive feedback loop. More hydrogen sulfide rises, consumes more oxygen, makes the water more acidic, which kills more organisms which sink and decompose, which uses up more oxygen, which allows more anaerobic bacteria to thrive, which produces more hydrogen sulfide. Round and round it goes, accelerating, spreading, until entire ocean basins become dead zones. This is not theoretical. This has happened multiple times in Earth's history, and we have found the evidence. During the late Devonian period, 375 million years ago, ocean anoxic events killed 75% of all species. The extinction happened in pulses, each pulse corresponding to another expansion of the dead zones. We have found rocks from this time period stained purple and green. We have found chemical markers that can only come from hydrogen sulfide. And we have found the fossil record showing wave after wave of extinction in the oceans. The Torsian event, 183 million years ago, was another massive ocean anoxic event. Carbon dioxide from volcanic eruptions warmed the planet. The oceans lost oxygen. Hydrogen sulfide accumulated. Marine ecosystems collapsed. We know this happened because geologists have drilled into ocean sediments and found layers of black shale, rock formed from organic matter that accumulated in oxygen-poor water. These black shale layers are like tombstones marking moments when the oceans died. Now, let me tell you what is happening right now in our modern oceans. There are already over 400 documented dead zones in coastal waters around the world. The largest is in the Gulf of Mexico, created by fertilizer runoff from farms in the American Midwest. The fertilizer washes into rivers, flows down the Mississippi, and enters the Gulf. The nutrients cause massive blooms of algae. When the algae die, they sink and decompose. The decomposition uses up all the oxygen in the water. Fish and shrimp flee the area or die. An area the size of Connecticut becomes lifeless every summer. The Baltic Sea has a massive dead zone. The Black Sea has one. The coasts of Oregon and Washington experience seasonal dead zones. These are not ancient history. This is happening now. And these dead zones are growing. As the planet warms, as agricultural runoff increases, as ocean circulation slows, the dead zones expand. Scientists who study modern oceans are seeing warning signs that deeply trouble them. The deep waters of the Pacific and Indian Oceans are losing oxygen measurably year by year. The process is slow, but it is consistent. Models predict that by the end of this century, large areas of the deep ocean could become anoxic. We are watching the early stages of what could become an ocean anoxic event. Here is what keeps oceanographers awake at night. Once these feedback loops start, they can be extremely difficult to stop. You cannot just turn off ocean warming like flipping a switch. The oceans have enormous heat capacity. They absorb heat slowly and release it slowly. Even if we stopped all carbon emissions today, the oceans would continue warming for decades because of heat already absorbed. That warming would continue to drive oxygen loss. Furthermore, we do not fully understand all the tipping points. At what temperature does the thermohaline circulation collapse entirely? At what oxygen level do anaerobic bacteria take over irreversibly? How much hydrogen sulfide can the oceans produce before it starts poisoning the atmosphere on a global scale? We have theories and models, but we have never watched a modern ocean die. Our data comes from rocks and fossils, from events millions of years ago. We are trying to predict the future based on fragmentary evidence from the deep past. Personal stories help us understand the human dimension of this crisis. There is an oceanographer named Dr. Lisa Levin who has spent decades studying oxygen minimum zones in the ocean. These are naturally occurring regions where oxygen is very low, though not completely absent. She has watched these zones expand over her career. She has documented species moving into shallower water to escape the spreading low oxygen areas. She has seen ecosystems shift and change. And she has warned repeatedly that we are playing with forces we do not fully understand. In her research, Dr. Levin has found creatures adapted to very low oxygen that are now leaving areas they have inhabited for thousands of years. If conditions are bad enough that even oxygen minimum zone specialists are fleeing, that tells you something dire is happening. These are the canaries in the coal mine, early warning signals that the ocean is in distress. Another researcher, Dr. Andrew Knoll from Harvard, studies ancient extinction events and compares them to modern changes. He has pointed out that the rate of ocean acidification today is faster than during the Great Dying. The oceans are absorbing carbon dioxide from the atmosphere, which makes them more acidic. This acidification dissolves the shells of plankton and corals. These creatures are the foundation of marine ecosystems. If they fail, everything else fails with them. Dr. Knoll has said something that should chill every person on this planet. He said that based on the geological record, based on what happened in past extinction events, we are on a trajectory that could lead to another mass extinction. Not will, not definitely, but could. The mechanisms are the same. The warning signs are there. The question is whether we will recognize the danger in time and change course. The terrifying thing about ocean anoxic events is that they can persist for hundreds of thousands of years once they start. The torsion event lasted nearly 1 million years. The ocean anoxic events associated with the Great Dying persisted through multiple pulses over hundreds of thousands of years. These are not short-term disasters you can wait out. These are fundamental changes to how the planet functions that can last longer than the entire span of human civilization. Recovery from these events is slow and painful. When the oceans finally do recover, when circulation is restored and oxygen returns to the depths, life has to rebuild from tiny surviving populations. New species have to evolve to fill empty niches. Ecosystems have to reassemble from scratch. The process takes millions of years, literally millions. More time than humans have existed as a species. More time than our ancestors have been using tools. The recovery time from ocean anoxic events is measured on a scale that dwarfs all of human history. This brings us to a crucial realization. The oceans are not just scenery. They are not just resources for fishing and shipping. They are life support systems for the entire planet. The oceans produce more than half the oxygen we breathe. They regulate global climate. They drive weather patterns. They feed billions of people. When the oceans are healthy, life thrives. When the oceans become anoxic and toxic, everything suffers. We are conducting an experiment right now. We are warming the planet faster than it has warmed in millions of years. We are changing ocean chemistry at unprecedented rates. And we're doing this while largely ignoring the lessons written in rocks from past extinction events. The rocks tell us exactly what happens when you rapidly warm the planet and acidify the oceans. They tell us the story ends with dead zones, poison gas, and mass extinction. But we are proceeding anyway, hoping somehow that this time will be different. But the oceans are not the only killer hiding beneath our feet. There is another threat, one that is more visible, more violent, and potentially just as deadly. A threat that has killed before and will kill again. A threat that we can monitor but cannot control. Chapter 8. The supervolcano beneath Yellowstone. Every year, 4 million tourists visit Yellowstone National Park in the northwestern United States. They come to see geysers shooting boiling water into the air. They photograph bison grazing in meadows. They hike through forests and marvel at colorful hot springs. Most of them have no idea they're walking on top of a bomb. Beneath Yellowstone lies a chamber of molten rock 55 miles long, 35 miles wide and several miles deep. This is not a normal volcano. This is a supervolcano, a volcanic system so massive that when it erupts, it does not build a mountain. It collapses, creating a crater that can swallow entire mountain ranges. Let me help you understand the scale we are talking about. When most people think of volcanoes, they picture something like Mount St. Helens. In 1980, Mount St. Helens erupted explosively, blowing off the entire north face of the mountain. The blast was heard over 200 miles away. Ash fell across Washington state and beyond. 57 people died. It was one of the most destructive volcanic eruptions in modern American history. The amount of material ejected was about 1 cubic kilometer. A Yellowstone supereruption would eject 2,500 cubic kilometers of material. Not twice as much as Mount St. Helens, not 10 times as much, 2,500 times as much. The difference is so vast it is almost impossible to comprehend. Trying to compare Mount St. Helens to Yellowstone is like comparing a firecracker to a nuclear bomb. We know Yellowstone can do this because it has done it before. 3 times in the last 2 million years, Yellowstone has exploded with cataclysmic force. The most recent eruption was 640,000 years ago. The eruption before that was 1.3 million years ago, and the one before that was 2.1 million years ago. Do you see the pattern? Roughly every 600,000 to 800,000 years, Yellowstone erupts, and it has been 640,000 years since the last eruption. We are right in the window when another eruption could occur. Now, before you panic, I need to tell you that volcanologists see no signs of an imminent eruption. The ground is not rapidly inflating. The earthquake swarms are normal. The gas emissions are within typical ranges. When volcanologists say imminent, they mean within the next few decades or centuries. In geological terms, imminent can mean within the next 100,000 years. So we are probably safe for our lifetimes and many lifetimes to come. But probably is not the same as definitely. And we need to understand what would happen if Yellowstone erupted, because it will erupt eventually. Maybe in 1,000 years, maybe in 50,000 years, maybe tomorrow. We simply do not know. Let me walk you through a Yellowstone super eruption, step by step. First, you would notice increasing earthquake activity. Not just 1 or 2 tremors, but hundreds, then thousands of earthquakes over days or weeks. This would be the magma forcing its way upward, cracking rock, making space for itself. The ground across Yellowstone would begin to bulge upward, rising by feet or even yards as magma accumulated beneath the surface. Geysers would change their behavior. Some would stop erupting. Others would become more violent. new hot springs would open up. The thermal features that make Yellowstone beautiful would become chaotic and dangerous. Steam explosions would start occurring randomly as superheated water flashed to steam. And then, with little final warning, the ground would split open. But this would not be a single vent like a normal volcano. This would be dozens of vents opening simultaneously across tens of miles. Magma would blast out of these vents at supersonic speeds, faster than the speed of sound, driven by the tremendous gas pressure that had built up over millennia. The eruption column would shoot 30 miles into the sky, higher than commercial aircraft fly, punching through the stratosphere into the mesosphere. The column would be so hot it would glow, visible from space as a pillar of fire. Ash and rock fragments called tephra would rain down across Wyoming, Montana, and Idaho within the first hour. The weight of this falling material would collapse buildings. A few inches of ash is heavy enough to cave in a roof. A foot of ash would crush most structures. Within 300 miles of Yellowstone, the ash fall would be measured in feet, burying everything, making the region completely uninhabitable. But the ash would not stop there. High-altitude winds would carry fine particles thousands of miles. Within 3 days, ash would be falling across the entire central and eastern United States. Cities like Denver, Kansas City, Chicago, and even New York would receive measurable ashfall. Airports would close. Roads would become impassable. The ash is not like snow. You cannot just melt it away. It is made of tiny glass shards that destroy engines, contaminate water supplies, and cause severe respiratory problems when breathed. The immediate death toll from ashfall, building collapses, and pyroclastic flows near Yellowstone could be in the hundreds of thousands. But that would just be the beginning. The real disaster would unfold over the following months and years. Remember our discussion of volcanic winters? A Yellowstone super-eruption would inject so much sulfur dioxide into the stratosphere that it would create a global cooling event. The sulfur dioxide would react with water vapor to form sulfuric acid droplets that reflect sunlight back into space. Global temperatures could drop by 10 to 15 degrees for several years. Agriculture across North America would collapse. The growing season would shorten dramatically. Crops would fail. Even regions that did not receive heavy ashfall would experience killing frosts in summer. Food shortages would develop within months. The United States produces a significant fraction of the world's grain. If American agriculture fails, the entire global food system is at risk. The economic impact would be catastrophic. The United States would suffer infrastructure damage in the trillions of dollars. International trade would be disrupted. Stock markets would crash. And remember, this is happening in a modern, interconnected world where supply chains are fragile, and just-in-time delivery is the norm. We do not stockpile food for years anymore. Most developed countries have only a few months of food reserves. A multi-year agricultural disruption could lead to famine on a scale humanity has never experienced. Now, Yellowstone is not the only supervolcano we need to worry about. There are at least 20 known supervolcanic systems on Earth. Lake Toba in Indonesia erupted 74,000 years ago in what might have been the largest volcanic eruption in the last 2 million years. The eruption ejected an estimated 2,800 cubic kilometers of material. Some scientists believe this eruption nearly drove humanity to extinction. At that time, modern humans had only recently evolved. Our population was small, perhaps numbering in the tens of thousands. The Toba eruption triggered a volcanic winter that lasted for years. Temperatures plummeted, food sources disappeared. Genetic evidence suggests that the human population crashed to perhaps as few as 3,000 breeding pairs. We came within a whisper of going extinct before we had even spread across the globe. We survived, obviously, but it was a close call. Campi Flegrei, near Naples, Italy, is another supervolcano that shows signs of unrest. The ground there has been rising and falling for decades. The region experiences frequent earthquake swarms. 40,000 years ago, Campi Flegrei produced an eruption that devastated the entire Mediterranean region. If it were to erupt today, millions of people living in the Naples area would be at immediate risk. The Taupo volcanic zone in New Zealand has produced multiple super-eruptions in the past 100,000 years. The most recent was just 1,800 years ago, relatively recent in geological terms. That eruption was smaller than a full-scale super-eruption, but still ejected 120 cubic kilometers of material, devastating the local area. What can we do about supervolcanoes? The honest answer is not much. We cannot stop them, we cannot prevent them. We can only monitor them and hope for enough warning to evacuate people from the immediate danger zone. Volcanologists use a variety of tools to watch these systems. They measure ground deformation with GPS instruments. They monitor seismic activity with networks of seismometers. They analyze gases being released to detect changes in the magma below. They use satellites to detect heat anomalies and ground movement. This monitoring gives us some comfort. The signs of an approaching super-eruption would build over months, or more likely years. It would not happen completely without warning. But the warning time might only be enough to evacuate the immediate area, not nearly enough time to prepare society for the global consequences. There is some fascinating and controversial research into whether we might be able to diffuse a supervolcano by drilling into it and allowing pressure to release gradually. The idea is that if you could release the gases slowly over decades, you might prevent a catastrophic explosion. But this idea has massive problems. First, drilling into a magma chamber is incredibly dangerous. You could trigger the very eruption you are trying to prevent. Second, these systems are so large that any drilling we could do would be like trying to deflate a hot air balloon by poking it with a pin. The scale does not match up. And third, we do not understand these systems well enough to know whether intervention would help or make things worse. So for now, we watch and we wait. We know these systems will erupt eventually. We know the consequences will be severe. But we do not know when, and that uncertainty is perhaps the most unsettling part of all. Supervolcanoes remind us that Earth is not a stable, peaceful place. It is a dynamic, violent planet where the ground itself can turn against us with little warning. But at least supervolcanoes are Earth-based threats. We can monitor them. We can study them. The threats from space are far more unpredictable and potentially far more deadly. Chapter 9. When stars explode. Look up at the night sky. Find the constellation Orion, the Hunter. In the upper left shoulder of Orion, you will see a bright reddish star. This is Betelgeuse, one of the largest stars visible to the naked eye. If you placed Betelgeuse at the center of our solar system, its surface would extend past the orbit of Jupiter. It is a red supergiant, a star in the final stages of its life, and it is going to explode. Not might, not could, will. The only question is when. When Betelgeuse explodes, it will become a supernova, one of the most energetic events in the universe. For a few weeks, this single star will outshine the entire galaxy it resides in. From Earth, 650 light-years away, it will be as bright as the full moon. You will be able to see it during the day. It will cast shadows at night. The explosion will be visible for months before fading. But here is the unsettling part. Light travels at 186,000 miles per second, and Betelgeuse is 650 light-years away. That means, when we look at Betelgeuse, we are seeing it as it was 650 years ago. The star might have already exploded in the year 1374, and the light from that explosion is racing toward us right now, due to arrive any day. Or it might explode tomorrow. Or it might last another 100,000 years. We simply do not know. Now, before you worry, Betelgeuse is far enough away that it poses no threat to Earth. The radiation from the supernova will be intense, but at that distance it will be harmless. We will get a spectacular light show and nothing more. But Betelgeuse helps us understand what can happen when massive stars die, and not all dying stars are as far away as Betelgeuse. Let me explain what happens inside a massive star. Stars are giant fusion reactors. In their cores, hydrogen atoms are crushed together by immense gravity and heat, fusing into helium and releasing energy. This energy creates outward pressure that balances the inward pull of gravity. As long as fusion continues, the star is stable. But fusion requires fuel, and eventually that fuel runs out. A star like our Sun will fuse hydrogen for about 10 billion years total. Our Sun is currently halfway through its life. When it finally runs out of hydrogen, it will swell into a red giant, swallow the inner planets including Earth, and then collapse into a white dwarf. It will not explode. But massive stars more than 8 times the mass of our Sun, have a different fate. They burn through their fuel much faster because their gravity is stronger, which creates higher core temperatures, which speeds up fusion. A star 20 times the mass of the Sun might live only 10 million years instead of 10 billion. It burns bright and dies young. When a massive star exhausts its hydrogen, it begins fusing helium into heavier elements. Then it fuses those heavier elements into even heavier ones. Carbon, oxygen, neon, silicon, each stage of fusion happening faster than the last. The star develops a layered structure like an onion, with different elements fusing in different shells. At the very center, the star begins producing iron. And this is where everything goes catastrophically wrong. Iron is the ultimate dead end in fusion. Fusing iron does not release energy, it absorbs energy. As soon as a massive star's core fills with iron, fusion stops. The outward pressure that was balancing gravity disappears. And in less than a second, literally less than 1 second, the entire core of the star collapses. The core, which might be as large as Earth, collapses down to a sphere only 12 miles across. The density becomes so extreme that protons and electrons are crushed together to form neutrons. What remains is called a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. The collapse happens so fast that the outer layers of the star do not have time to fall inward. They are still hanging in space when the core has already collapsed. Then the bounce happens. The infalling matter hits the incompressible neutron star and rebounds like a ball bouncing off concrete. This rebound sends a shock wave outward through the star at a significant fraction of the speed of light. The shock wave blasts the outer layers of the star into space in an explosion so powerful it can be seen across the entire universe. This is a supernova. The explosion releases more energy in a few seconds than our Sun will produce in its entire lifetime. The light from the explosion can briefly outshine billions of stars combined. And this is where it becomes dangerous for life on nearby planets. The supernova does not just release visible light, it releases radiation across the entire electromagnetic spectrum. X-rays, gamma rays, ultraviolet radiation, all of it streaming outward in a spherical shell, expanding at close to light speed. Any planet within 50 light-years is in the danger zone. If a supernova occurred within 50 light-years of Earth, here is what would happen. First, the visible light would arrive, turning night into day for weeks. Then the radiation would hit. High-energy gamma rays and X-rays would slam into Earth's atmosphere. The interaction would create massive amounts of nitrogen oxides, the same chemicals that destroyed the ozone layer during the Ordovician extinction. Within weeks, our ozone layer could be half destroyed. Ultraviolet radiation from the sun would spike to lethal levels. Skin cancer rates would skyrocket. Plants would suffer severe damage. Plankton in the ocean would die from UV exposure. The base of the food chain would collapse. And remember, the radiation would not last for just a few days. The ozone layer takes years to recover. We would face years of elevated radiation, years of agricultural disruption, years of ecosystem collapse. Have we been hit by nearby supernovas in Earth's past? Scientists believe so. Remember the Ordovician extinction 450 million years ago? The extinction that killed 85% of ocean species? Some scientists think it was caused by a supernova or gamma-ray burst that stripped away our ozone layer. The evidence is circumstantial but compelling. We see the signs of ozone destruction. We see radiation damage to spores and pollen. And we see a sharp spike in certain isotopes that could only have come from a nearby stellar explosion. More recently, about 2 to 3 million years ago, there was a series of supernovas in our cosmic neighborhood. We know this because scientists have found iron-60 in deep-sea sediments from that time period. Iron-60 is a radioactive isotope that does not occur naturally on Earth. It has to come from space, specifically from supernova explosions. The presence of iron-60 tells us that supernovas occurred close enough to sprinkle their debris across Earth. These supernovas may have contributed to climate changes that affected our early ancestors. Some scientists speculate that increased cosmic radiation from these explosions may have even influenced human evolution, increasing mutation rates and driving evolutionary change. This is highly speculative, but it shows how intimately connected we are to cosmic events. Today, astronomers have identified several stars that could go supernova and are close enough to affect Earth. I mentioned Betelgeuse, but that one is actually too far away to hurt us. The more worrying candidates are stars like Spica, Ike Pegasi and Antares. These stars are anywhere from 150 to 600 light-years away. If they exploded, they might be close enough to cause problems, but probably not. The danger zone is really only out to about 50 light-years, and thankfully there are no supernova candidates that close. But supernovas are not the only stellar threat. There is something even more dangerous, something we discussed at the very beginning. Gamma-ray bursts. These are like supernovas on steroids. While a supernova releases its energy in all directions, a gamma-ray burst focuses most of its energy into two narrow beams, like cosmic death rays shooting out from the poles of the dying star. If you are anywhere in the path of one of these beams, even thousands of light-years away, you are in mortal danger. The gamma-ray burst would deliver as much energy as being just a few light-years from a regular supernova, but from a vastly greater distance. Gamma-ray bursts are the ultimate long-range killers. The terrifying thing about gamma-ray bursts is that they travel at the speed of light. You would have zero warning. The first photons of the burst would arrive at exactly the same time as the visible light from the explosion. One moment, your sky looks normal, and the next moment, you are being hit by a wave of radiation intense enough to sterilize a hemisphere. We detect gamma-ray bursts happening in distant galaxies every single day. They are common in the universe. But our galaxy is large and space is vast, so the odds of one hitting Earth are low. Scientists estimate that a gamma-ray burst capable of causing a mass extinction might hit Earth once every billion years or so. Not impossible, but not likely in any time frame relevant to human civilization. There is one more stellar threat worth mentioning: solar storms. Our own Sun, despite being a relatively calm and stable star, occasionally erupts. The Sun's surface is covered in magnetic field lines that twist and tangle due to the Sun's rotation. Sometimes these field lines snap, releasing enormous amounts of energy in an event called a solar flare. Even larger releases occur during coronal mass ejections, where billions of tons of plasma are hurled into space. Most of these events miss Earth. Space is big and we are a small target. But every few decades we get hit by a significant solar storm. In 1859, the largest solar storm in recorded history struck Earth. It is called the Carrington event, named after the astronomer who observed the solar flare that caused it. The Carrington event was so powerful that auroras were visible as far south as the Caribbean. Telegraph systems worldwide went haywire. Some telegraph operators reported receiving electric shocks. Some telegraph wires actually sparked and caught fire. Telegraph messages could be sent even with the power disconnected because the storm induced so much electricity in the wires. This happened in 1859, when our technological infrastructure was primitive. Imagine the same storm hitting today. Every satellite in orbit would be fried. GPS would fail. Communication satellites would go offline. The International Space Station would be in grave danger, its electronics destroyed, its astronauts exposed to lethal radiation doses. On the ground, the induced electrical currents would surge through power grids, destroying transformers that take months to replace. Large portions of the world could lose electricity for years. Some scientists estimate that a Carrington-level event hitting today could cause trillions of dollars in damage and set back technological civilization by decades. And we know such storms happen roughly once every 500 years. We are overdue for another one. In fact, in 2012, a Carrington-level solar storm missed Earth by only 9 days. If it had hit, we would still be recovering. The good news is that we can see solar storms coming. We have satellites monitoring the sun constantly. When a major coronal mass ejection is aimed at Earth, we get about 12 to 24 hours warning. That is not enough time to do much, but we can shut down satellites to protect them, disconnect high-voltage transformers to prevent damage, and alert astronauts to take shelter. The warning time might save our technological infrastructure from total destruction, even if we cannot prevent all damage. Space is not empty and peaceful. It is a violent place filled with explosions, radiation, and objects moving at incredible speeds. We live in this environment, shielded only by a thin atmosphere and a magnetic field. We are lucky that the really dangerous stellar events are rare, and that the most common threats like solar storms give us at least some warning. But there is one threat from space that combines the destructive power of stellar events with the inevitability of planetary mechanics. A threat that does not depend on chance or bad luck. A threat that is written into the very orbits of objects in our solar system. A threat that will strike Earth again, and we have found thousands of these threats already, with more being discovered every year. Chapter 10. The Asteroid Next Door. Let me take you on a journey to a place most people never think about, a place that holds the key to understanding one of humanity's greatest threats. We're going to visit the asteroid belt, a region of space between Mars and Jupiter filled with millions of chunks of rock and metal left over from the formation of the solar system. 4.5 billion years ago, when the Sun and planets were forming, the region between Mars and Jupiter should have coalesced into a planet. There was plenty of material there. But Jupiter's immense gravity stirred things up, accelerating the rocks to such high speeds that when they collided, they shattered instead of sticking together. The result is a vast donut-shaped region filled with asteroid fragments ranging in size from dust grains to objects hundreds of miles across. Now, despite what science fiction movies show, the asteroid belt is mostly empty space. If you flew a spacecraft through it, you would probably not see any asteroids up close. They are spread out over such enormous distances that they are essentially invisible to each other most of the time. But there are so many of them, and they have been bouncing around for so long, that collisions happen regularly. When two asteroids collide, they shatter into smaller pieces, and those pieces go flying off in new directions with new orbits. Some of those new orbits cross paths with Earth. These objects are called near-Earth objects, and they are the ones that keep astronomers awake at night. We have currently identified about 10,000 near-Earth asteroids larger than 140 meters across. But scientists estimate there are over 25,000 of them out there. We have found less than half. Let me help you understand what different-sized asteroids can do. An asteroid about 20 meters across, roughly the size of a house, explodes in Earth's atmosphere about once per year. Most of these explode over oceans or unpopulated areas and go unnoticed. But remember the 2013 explosion over Russia we discussed earlier? That asteroid was only 60 feet across, and it injured 1,500 people from flying glass. An asteroid 140 meters across, about the length of 1.5 football fields, could destroy an entire city. If it hit near a populated area, it could kill millions. Objects this size hit Earth roughly once every 20,000 years. That sounds like a long time, but remember there are thousands of these objects we have not found yet. One of them could be heading toward us right now. An asteroid 1 kilometer across, 0.6 of a mile, could trigger a regional catastrophe. The explosion would be equivalent to thousands of nuclear weapons. It would throw up enough dust to cause global crop failures for years. Civilization would survive, but billions could die from famine and economic collapse. These hit Earth roughly once every 500,000 years. And then there are the dinosaur killers, asteroids 5 to 10 kilometers across. These cause mass extinctions. They hit Earth roughly once every 100 million years. The good news is we have found almost all of them. The bad news is almost is not the same as all. Now let me tell you about one specific asteroid that gave astronomers a heart attack. In 2004, scientists discovered an asteroid they named Apophis, after the Egyptian god of chaos. Initial observations suggested it was on a collision course with Earth, with impact predicted for April 13, 2029. The calculated odds were initially about 2.7%, which in astronomical terms is terrifyingly high. Further observations refined the orbit and showed that Apophis would miss Earth in 2029, but just barely. It will pass within about 19,000 miles of Earth's surface, closer than our geosynchronous satellites. When Apophis makes this pass, Earth's gravity will actually change its orbit, pulling it into a new trajectory. Scientists are still calculating whether this gravitational interaction might set up a collision in a later year, possibly 2068. Apophis is about 1,200 feet across. Not a dinosaur killer, but definitely big enough to destroy a large city or trigger massive tsunamis if it hit the ocean. The fact that we did not discover it until 2004, just 25 years before its close approach, should terrify everyone. If it had been on a collision course, we would have had very little time to prepare. This brings us to the critical question: what would we do if we found an asteroid heading toward Earth? This is not science fiction anymore. This is a real question that NASA and other space agencies have been working on for decades. The first and most important step is detection. We need to find dangerous asteroids decades before they hit, not years. This requires building more and better telescopes dedicated to asteroid hunting. Currently, we have several programs doing this. The Catalina Sky Survey, Pan-STARRS, and the new Vera Rubin Observatory are all scanning the skies every night, looking for faint moving objects that might be asteroids on dangerous orbits. But finding them is only half the battle. Once you find a dangerous asteroid, you need to deflect it. And this is where things get interesting, because we have actually tested this capability for the first time in human history. Chapter 11. DART Mission: Humanity Fights Back. On November 24, 2021, a small spacecraft the size of a vending machine launched from Vandenberg Space Force Base in California. Its destination was an asteroid system located about 7 million miles from Earth at the time of impact. The mission was called DART, which stands for Double Asteroid Redirection Test, and it represented something unprecedented in human history. For the first time ever, we were going to deliberately crash into an asteroid to see if we could change its orbit. The target was an asteroid named Dimorphos, which is Greek for two forms. Dimorphos is actually a moon orbiting a larger asteroid named Didymos. The whole system is like a miniature Earth-Moon system, except tiny. Didymos is about 2,600 feet across, while Dimorphos is only 525 feet across, about the size of the Great Pyramid of Giza. Why target a moon instead of a solitary asteroid? Because it gives us an easy way to measure success. When Dimorphos orbits Didymos, it periodically passes in front of the larger asteroid from our viewpoint, causing a slight dimming that we can detect with telescopes. By timing these mini eclipses, we can calculate the orbital period very precisely. If we hit Dimorphos hard enough to change its orbit, we will see that orbital period change. The DART spacecraft spent almost a year traveling through space. It did not take a direct path. Instead, it looped around using gravitational assists and careful trajectory planning. As it approached the target, the spacecraft was moving at about 14,000 miles per hour relative to Dimorphos. At that speed, even a small spacecraft becomes a devastating projectile. The final hours of the mission were nerve-wracking. Engineers at Johns Hopkins Applied Physics Laboratory watched as DART's camera began to resolve Dimorphos from a point of light into an actual object. As the spacecraft got closer, details emerged. Dimorphos was not smooth. It was covered in boulders, some as large as houses. The surface was rough and irregular, shaped by billions of years of micrometeorite impacts. DART was navigating autonomously. It was too far from Earth for real-time control. Radio signals take seconds to travel even relatively short distance in space. By the time engineers saw where the spacecraft was, that information was already outdated, so DART had to find and hit the asteroid on its own using sophisticated computer vision and navigation algorithms. In the final minutes, images were streaming back to Earth every second. The asteroid grew larger and larger in the frame. Engineers and scientists watching the feed could see individual boulders. They could see the shadows cast by Didymos, the larger asteroid, visible in the background. And then, at the last moment, the image froze. DART had impacted Dimorphos at precisely the speed and angle intended, but the scientists did not know immediately if it had worked. They needed to wait and make very precise measurements of Dimorphos's orbit to see if it had changed. Ground-based telescopes around the world swung into action, timing the orbital period with incredible precision. And a few days later, the results came in. Success. DART had changed Dimorphos's orbital period by 33 minutes. They had been hoping for a change of just 10 minutes. The impact was more effective than predicted. Why? When DART hit, it did not just transfer its momentum to the asteroid. It created a crater and threw out a plume of debris. This debris acted like the exhaust from a rocket, providing additional thrust that pushed the asteroid further than expected. This is called the ejector enhancement effect, and it means that kinetic impactors might be even more effective than we thought. Let me help you understand why this matters. Changing an orbit by 33 minutes does not sound like much, but remember, orbits are circles or ellipses that objects follow again and again. If you change the orbit even slightly, that change compounds over time. After one orbit, Dimorphos is 33 minutes off from where it would have been. After 10 orbits, it is 10 times 33 minutes off. The deviation grows and grows. If we had decades of warning about a dangerous asteroid, even a small nudge would be enough to make it miss Earth entirely. Imagine an asteroid is going to hit Earth 20 years from now. Its orbit is such that it will intersect Earth's orbit at precisely the moment Earth is at that point in space. But if we can change the asteroid's orbital period by just a few minutes, then 20 years from now, when the asteroid reaches that intersection point, Earth will have already passed by, or Earth will not have gotten there yet. Either way, no collision. The key insight is that asteroid deflection is not like the movies. We do not need to blow up the asteroid at the last second. We need to nudge it gently many years in advance. It is the difference between trying to stop a train by standing in front of it versus switching the tracks miles ahead of time. One approach is impossible and suicidal. The other is practical and effective. The DART mission proved that the kinetic impactor technique works. We can hit asteroids with spacecraft moving at high speeds, and we can change their orbits measurably. This is not speculation anymore. This is demonstrated capability. Humanity has now deflected an asteroid. It was a small one, and it was not actually threatening Earth, but we proved we can do it. But kinetic impact is not the only technique we have considered. Scientists have proposed numerous other methods for deflecting dangerous asteroids, each with advantages and disadvantages depending on the situation. The gravity tractor is one elegant solution. Instead of crashing into the asteroid, you park a spacecraft near the asteroid and just let gravity do the work. Every object with mass has gravity. Even a small spacecraft has a tiny gravitational pull. If you station a spacecraft next to an asteroid and fire thrusters to keep it in position, the spacecraft's gravity will gradually pull the asteroid toward it. Over months or years, this gentle pull can change the asteroid's orbit significantly. The advantage of the gravity tractor is that it is gentle and predictable. You can precisely control how much you deflect the asteroid. The disadvantage is that it is slow. You need years or decades of warning time. And keeping a spacecraft stationed next to an asteroid for that long requires fuel, power, and incredibly precise navigation. Another proposed method involves painting the asteroid. Yes, painting it. The idea is that if you cover one side of the asteroid with reflective paint or dust, that side will reflect more sunlight. The reflected photons carry momentum, and over time this creates a small but steady push. It is like using sunlight as a very weak rocket engine. This would only work for small asteroids with decades of warning time, but it has the advantage of requiring very little energy once the paint is applied. And then there is the nuclear option. Literally. If we discovered an asteroid heading toward Earth and we had only a few months of warning, our best option might be to hit it with a nuclear weapon. Not to blow it up, despite what Hollywood tells us. Blowing up an asteroid just turns one big problem into many smaller problems, and those fragments can still hit Earth. Instead, you would detonate the nuclear weapon near the asteroid, not touching it. The explosion would vaporize part of the asteroid's surface, and that vaporized material would act like rocket exhaust, pushing the asteroid in the opposite direction. A nuclear deflection could provide a much bigger push than a kinetic impactor, but it is also much harder to control and predict. The good news is that we have these options. The bad news is that they all require warning time. And warning time depends on finding the asteroids before they get too close. This is why NASA and other space agencies are investing heavily in sky surveys. The goal is to find 90% of all near-Earth asteroids larger than 140 meters by the early 2030s. But even with the best detection systems, there is a limit to how much warning we can get. Some asteroids, like the one that exploded over Russia in 2013, approach from the direction of the Sun. Our telescopes are blinded by the Sun's glare. We simply cannot see objects coming from that direction until they are almost upon us. There is a proposed solution. Put a telescope in space positioned between Earth and the Sun. This telescope would have a clear view of the sunward sky and could detect asteroids we cannot see from Earth. Such a mission has been proposed several times, but has not yet been funded. It is a prime example of how planetary defense is still not taken as seriously as it should be. Let me put this in perspective. We spend trillions on military defense worldwide. We spend billions on cybersecurity. but we spend only a few $100 million per year on defending against asteroid impacts. Yet an asteroid impact could kill more people than any war and do more damage than any cyber attack. The threat is real, the consequences are catastrophic, and the technology to prevent it exists. We just need the will and funding to implement it. The DART mission cost about $300 million. That sounds like a lot, but it is less than the cost of a single modern fighter jet. And unlike a fighter jet, DART benefits all of humanity, not just one nation. Asteroid defense is one area where international cooperation is not just beneficial, but essential. An asteroid does not care about national borders. If one is heading toward Earth, we all need to work together to stop it. Now, after talking about all these extinction threats from space and from Earth, after discussing gamma-ray bursts and supervolcanoes and ocean anoxic events, I need to tell you about the most likely extinction event we face. The one that is happening right now. The one that we are causing. Chapter 12. The extinction we're causing. There is an extinction event unfolding at this very moment. You cannot see it in a single dramatic moment like an asteroid impact. You cannot point to a specific day when it started. But if you zoom out and look at the data, the evidence is undeniable. We are living through the sixth mass extinction in Earth's history, and unlike all the others, this one is being caused by a single species, US. Let me show you the numbers, because numbers do not lie. Under normal background conditions, the extinction rate is about 1 to 5 species per year per million species on Earth. This is natural. Species go extinct. New species evolve. It is part of the normal churn of life. But today, species are going extinct at a rate of 1,000 to 10,000 times faster than the background rate. We are losing species at a pace not seen since the asteroid killed the dinosaurs. Since the year 1500, we have documented the extinction of at least 870 species. But that is just the ones we knew about and could confirm. The actual number is certainly much higher. Many species went extinct before we even discovered them. Many more are functionally extinct, with populations so small they cannot recover. Here is what makes this particularly heartbreaking. The extinctions are accelerating. In the last 50 years, we have lost more species than in the previous 450 years. The rate is increasing, not decreasing. And current projections suggest that we could lose up to 1 million species in the next few decades. That is 1 million species that will never exist again. 1 million unique products of billions of years of evolution erased. What is killing them? The causes are numerous, but they all trace back to human activity. Let me walk you through the main killers. First, habitat destruction. This is the biggest driver of extinction. Every year, we clear an area of forest the size of Greece. Forests are not just trees. They are ecosystems containing thousands of interconnected species. When you clear a forest, you do not just remove the trees. You eliminate the habitat for birds, insects, mammals, reptiles, amphibians, fungi, and countless other organisms. Many of these species exist nowhere else. When their forest is gone, they are gone. The Amazon rainforest is the most biodiverse place on Earth. It contains an estimated 10% of all species on the planet, and we are cutting it down at a rate of millions of acres per year for cattle ranches and agriculture. Every day, dozens of species that we have never even named are going extinct because their small patch of rainforest was cleared. Second, climate change. We have already discussed how warming triggers extinction events. We have seen what happened during the Great Dying, when volcanic eruptions released greenhouse gases and warmed the planet. We are doing the same thing today, but at an even faster rate. Since the Industrial Revolution, we have released billions of tons of carbon dioxide into the atmosphere by burning fossil fuels. Global temperatures have risen by about 2 degrees so far, and they are on track to rise by 4 to 5 degrees by the end of this century if we do not change course. This might not sound like much, but remember, during the Great Dying, temperatures rose by 18 degrees and killed 96% of species. We are on a trajectory towards similar warming if we include all feedback loops and tipping points. Many species cannot adapt fast enough. Coral reefs are bleaching and dying because ocean temperatures are rising. Polar bears are losing their sea ice hunting grounds. Alpine species are being pushed up mountains until they run out of mountain. Plants are trying to migrate toward the poles, but they cannot move fast enough, and many encounter barriers like cities and farmland that block their way. Third, pollution. We are poisoning the planet in countless ways. Plastic waste fills the oceans, breaking down into microplastics that accumulate in every living thing. Chemical runoff from farms creates dead zones in coastal waters. Air pollution affects ecosystems on land and in water. Heavy metals from mining contaminate rivers and soil. We are conducting a giant, uncontrolled experiment in how much pollution ecosystems can tolerate before they collapse. Fourth, overfishing. We have removed 90% of large fish from the oceans. Cod, tuna, sharks, all of them exist at tiny fractions of their historical populations. We have scraped the ocean floor with bottom trawlers, destroying habitats that took thousands of years to develop. We have caught fish faster than they can reproduce. Many fish populations have crossed tipping points where they cannot recover even if we stopped fishing entirely. Fifth, invasive species. As humans travel the globe, we accidentally and sometimes deliberately carry species to new places. Without their natural predators and competitors, these species can run rampant. Rats brought by ships to islands have driven dozens of bird species extinct. Zebra mussels, introduced to the Great Lakes, have disrupted entire ecosystems. Pythons released in Florida are eating their way through the Everglades. Each invasive species creates a cascade of extinctions as native species are outcompeted or eaten. The scariest part? These drivers do not act independently. They work together, creating feedback loops that accelerate collapse. Habitat destruction makes species more vulnerable to climate change. Climate change makes invasive species more successful. Pollution weakens species, making them more susceptible to disease. The problems multiply. Let me tell you some personal stories, because extinction is not just about statistics. It is about individuals, about species with unique behaviors and adaptations that took millions of years to evolve. The Baiji River dolphin in China was declared extinct in 2006. These dolphins had lived in the Yangtze River for 20 million years. They survived ice ages and climate shifts, but they could not survive pollution, boat traffic, and overfishing. The last confirmed sighting was in 2002. The western black rhinoceros was declared extinct in 2011, killed for its horn, which is made of keratin, the same material as your fingernails. An entire subspecies of rhinoceros, an evolutionary lineage millions of years old, was erased because some people believe rhino horn has medicinal properties, despite zero scientific evidence supporting this. The Pyrenean ibex, a type of wild goat, went extinct in 2000. The last individual, a female named Celia, was found dead with a tree fallen on her. Scientists actually attempted to clone her using preserved tissue samples. The clone was born but died within minutes due to lung defects. It remains the only animal to go extinct twice. These are just 3 examples among hundreds. Each extinction is a tragedy. Each one represents a unique solution to the problem of survival, a unique set of genes, a unique place in the web of life, lost forever. But here is what makes this different from past extinctions. We know it is happening. We can see it in real time. We have the data. We understand the causes. And most importantly, we have the ability to stop it. Unlike the dinosaurs facing an asteroid, unlike the Permian creatures facing volcanic eruptions, we can actually prevent our own extinction event. Stopping habitat destruction means protecting more land and ocean, creating nature reserves, limiting logging and clearing, allowing damaged ecosystems to recover. Stopping climate change means transitioning to renewable energy, electrifying transportation, improving efficiency, and removing carbon from the atmosphere. Stopping pollution means better regulations, cleaner technology, and a shift away from a throwaway culture. Stopping overfishing means sustainable fishing practices, aquaculture improvements, and protected marine areas. Stopping invasive species means better biosecurity and active removal programs. None of this is impossible. None of it requires technology we do not have. It requires will. It requires recognizing that the current path leads to catastrophe and choosing a different path. Scientists have calculated that we need to protect at least 30% of Earth's land and oceans by 2030 to prevent the worst extinctions. Currently, we protect about 15% of land and 7% of oceans. We are halfway there on land and not even close in the oceans. But it is achievable if we commit to it. We also need to acknowledge something uncomfortable. The current extinction crisis is linked to inequality and overconsumption. The wealthiest 1 billion people on Earth are responsible for a disproportionate amount of resource consumption and environmental damage. Meanwhile, the poorest billion people, who contribute almost nothing to the crisis, suffer the worst effects. Any solution must address this imbalance. Here is the brutal truth. Every past mass extinction was followed by millions of years of recovery. Life bounced back. Evolution filled the empty niches with new species, but that recovery took time, enormous amounts of time. If we cause a mass extinction, we will not be around to see the recovery. Human civilization, possibly humanity itself, will be part of the extinction. We sometimes comfort ourselves by saying, life will find a way. And it is true that something will survive. Bacteria will persist. Some insects will make it. Rats will probably do fine. But the rich tapestry of biodiversity, the millions of species that make Earth vibrant and beautiful, that could be gone. And the question is, do we want to be the species that erased all that wonder? Do we want that to be our legacy? There is still time to change course, but that time is running out. Every year we delay makes the problem harder and the consequences more severe. The choice is ours, and it is a choice we must make now, not later. Because unlike asteroids that we can deflect with decades of warning, unlike volcanoes that give us years of increasing activity, the extinction crisis is happening right now, and the window to prevent the worst outcomes is closing. Chapter 13. Watching the Skies. Despite all the threats we face, despite the dangers lurking in space and beneath our feet, humanity is not defenseless. We have something no other species in Earth's history has ever had. We have knowledge, we have technology, and we have the ability to watch for threats and prepare for them. Let me take you inside the global network of systems we have built to monitor threats. This is humanity's early warning system, our planetary defense shield, and it is more sophisticated than most people realize. First, let us talk about asteroid detection. Around the world, dozens of telescopes scan the sky every single night, searching for moving objects. The Catalina Sky Survey in Arizona operates 2 telescopes that have discovered more near-Earth asteroids than any other program. They take multiple images of the same patch of sky separated by time. Anything that moves between images is potentially an asteroid. Sophisticated software analyzes these images automatically, flagging potential threats for human review. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System in Hawaii, uses some of the world's largest digital cameras to photograph huge swaths of sky. Every few nights, it images the entire visible sky. By comparing images over time, it can detect not just asteroids, but also comets and even distant supernovas. The newest and most powerful system is the Vera Rubin Observatory in Chile, which began operations recently. This observatory has a mirror 27 feet across and a camera with 3 billion pixels, the largest digital camera ever built for astronomy. It will photograph the entire southern sky every few nights, detecting objects 100 times fainter than previous surveys could see. Scientists estimate it will double the number of known asteroids in its first year of operation. When these systems detect a potential threat, the data goes to the Minor Planet Center, a central clearinghouse operated by the International Astronomical Union. The Minor Planet Center calculates orbits and assesses risk. If an asteroid's orbit shows even a small chance of hitting Earth, it gets flagged for additional observations. More telescopes swing into action, gathering more precise data. Within days or weeks, the orbit is refined enough to determine if there is a real threat or if it is a false alarm. Most are false alarms, but the system works. In 2008, astronomers detected a small asteroid 19 hours before it hit Earth. 19 hours is not much warning, but it was enough to predict where it would hit in the Sudan desert, and expeditions were able to recover meteorite fragments. This proved our detection systems can find even small objects before impact, if they come from the right direction. The problem, as we discussed, is objects coming from the direction of the Sun. Our telescopes are blind in that direction. That is why NASA is developing NEO Surveyor, a space telescope specifically designed to find asteroids. It will orbit near Earth, but positioned to have a clear view of the sunward sky. Launch is planned for the late 2020s. When operational, it will close the biggest gap in our detection network. Now, let us talk about volcanic monitoring. Around the world, hundreds of volcanoes are monitored constantly by networks of instruments. Seismometers detect earthquakes caused by magma movement. GPS stations measure ground deformation to detect when magma is accumulating. Gas sensors measure sulfur dioxide and carbon dioxide emissions, which increase when magma rises. Thermal cameras detect heat anomalies. Satellites measure tiny changes in the shape of the ground from space. At Yellowstone, the USGS operates one of the most sophisticated monitoring networks on Earth. More than 100 seismometers record every tiny earthquake. GPS stations check for ground movement to millimeter precision. Temperature probes monitor heat flow. If Yellowstone were preparing to erupt, scientists would know years in advance. The warning signs would be unmistakable. Thousands of earthquakes, rapid ground deformation, massive increases in gas emissions. The same monitoring exists at other supervolcanoes. Campi Flegrei near Naples is watched intensely because millions of people live nearby. Any signs of an imminent eruption would trigger evacuation plans. The monitoring systems have been tested during volcanic crises at places like Mount Pinatubo in the Philippines, where accurate forecasting allowed thousands of people to evacuate before the massive 1991 eruption. For solar storms, we have satellites positioned between Earth and the Sun. The most important is called SOHO, the Solar and Heliospheric Observatory. It watches the Sun continuously, detecting coronal mass ejections as they leave the solar surface. When a big one is heading toward Earth, SOHO gives us 12 to 24 hours warning. NASA and NOAA also operate other satellites that monitor the Sun and provide forecasts of space weather. The U.S. National Oceanic and Atmospheric Administration runs the Space Weather Prediction Center, which issues warnings just like weather forecasts. Power companies can prepare by disconnecting vulnerable transformers. Satellite operators can put spacecraft into safe modes. Astronauts on the International Space Station can shelter in more protected modules. Airlines can reroute flights to avoid polar routes where radiation exposure would be highest. For ocean monitoring, we have a fleet of robotic floats called the Argo network. Over 3,000 of these floats drift in oceans worldwide, diving deep and returning to the surface, measuring temperature, salinity, and other properties. Satellites monitor ocean color, which tells us about plankton populations. Other satellites measure sea surface temperature and sea level. This global network allows scientists to track ocean health in real time and detect concerning trends like expanding dead zones and declining oxygen levels. For climate monitoring, we have dozens of satellites measuring everything from atmospheric carbon dioxide to ice sheet thickness to forest cover. Ground stations monitor temperature, precipitation and wind. Ocean buoys track sea surface conditions. This massive data collection system allows scientists to track how the climate is changing with unprecedented precision. And here is something remarkable. All of this monitoring data is shared globally. Scientists from every country can access asteroid data, volcanic monitoring, climate measurements. This is one area where international cooperation actually works. Because these threats affect everyone, the data benefits everyone. But monitoring is only useful if we ACT on what we learn. This is where humanity sometimes fails. We have the data showing climate change is real and dangerous, but action has been slow. We know which volcanoes are most dangerous, but urban development continues near them. We find asteroids on potentially dangerous orbits, but funding for deflection missions is limited. The good news is that awareness is growing. A generation ago, asteroid deflection was science fiction. Now it is demonstrated technology. A generation ago, climate science was controversial. Now it is accepted by the vast majority of scientists and policymakers. We are slowly learning to take existential threats seriously. There is one category of threat, however, that we cannot monitor effectively. Things like gamma-ray bursts, rogue black holes, or fast radio bursts from unknown sources. These are the true unknown threats, the cosmic dangers we have not yet characterized fully. Every year, astronomers discover new phenomena in the universe that we do not understand. Some of them might be dangerous. We simply do not know. This is why fundamental astronomy research is so important. When we build bigger telescopes and study the universe, we are not just satisfying curiosity. We are learning about the environment we live in. We are identifying potential threats. Every discovery tells us more about the rules of the cosmos and helps us understand our place in it and the dangers we face. The James Webb Space Telescope, launched in 2021, is revealing the universe in unprecedented detail. It may discover new types of cosmic events we never knew existed. Some of them might be relevant to planetary survival. The more we learn, the better we can prepare. Despite all our technology and monitoring, we must remain humble. The universe is vast and full of surprises. We have only been seriously watching the sky for a few decades. Humans have only existed for a few 100,000 years. The universe is nearly 14 billion years old. We are newcomers trying to understand a cosmos that has been running according to its own rules for eons before we arrived. But being newcomers also means we bring a fresh perspective. We are the first species on Earth capable of understanding extinction threats. We are the first species capable of preventing them, at least some of them. That is an awesome responsibility and an incredible opportunity. Chapter 14. Survivors. Let me tell you a story about hope, about resilience, about the unstoppable force that is life itself. After the asteroid killed the dinosaurs, Earth was a wasteland. The sky was dark, the ground was covered in ash. Temperatures had plunged. 99% of living things were dead. If you could have stood on Earth 66 million and 1 years ago, you might have concluded that life on this planet was finished. But you would have been wrong. Somewhere in the ruins, in a burrow deep underground, a small furry creature emerged cautiously into the devastated world. It was a mammal, no bigger than a rat, with a long snout and a nervous demeanor. It had survived the impact winter by hiding, by eating whatever it could find, by being small enough that it did not need much food. This creature was one of our ancestors, and it was about to inherit the Earth. Over the next 1,000,000 years, that tiny mammal's descendants began to diversify. With the dinosaurs gone, ecological niches were empty. There were no large predators, no large herbivores, just opportunities stretching to every horizon. Evolution, given a blank canvas, began to paint. Some mammals grew larger, filling the roles once occupied by dinosaurs. Others stayed small, but became highly specialized. Some took to the trees, others took to the water. Within 10 million years, the world was filled with mammals of every imaginable shape and size. Horses, whales, bats, primates, all of them descended from that tiny rat-like survivor. This is the pattern we see after every mass extinction, after the devastation, after the dying, after the silence. Life returns. It returns with a vengeance, more diverse than before, more adaptable, more resilient. Extinction clears the stage, but evolution rushes to fill it with new actors. After the Great Dying 252 million years ago, when 96% of species vanished, recovery took longer. 10 million years before ecosystems fully rebuilt. But they did rebuild. And from that recovery came the dinosaurs, the most successful group of land animals ever to live, dominating the planet for 150 million years. After the Devonian extinction, when toxic oceans killed 3/4 of species, life bounced back. Fish evolved jaws and became more diverse than ever. The first four-legged animals crawled onto land, establishing vertebrate life on continents for the first time. The pattern is clear. Life is stubborn. Life persists. No matter how bad things get, something survives, and that something becomes the seed for everything that follows. This gives me hope, even in the face of the current extinction crisis. Because I know that no matter what humans do to this planet, life will continue. Maybe not US, maybe not the species we love and the ecosystems we depend on, but something will survive and eventually thrive. Let me tell you about the most resilient creatures on Earth. Tardigrades, also called water bears, are microscopic animals less than 1 millimeter long. They look like tiny 8-legged bears under a microscope, and they are virtually indestructible. Tardigrades can survive temperatures from near absolute zero to above the boiling point of water. They can withstand pressure 6 times greater than the deepest ocean trench. They can survive radiation doses that would kill a human 1,000 times over. They can even survive in the vacuum of space. In experiments, tardigrades have been frozen for 30 years and revived. They have been shot out of guns and survived the impact. They have been exposed to lethal doses of radiation and crawled away unharmed. These creatures are survivors in the truest sense. If there were a nuclear war, if there were an asteroid impact, if there were a gamma-ray burst, tardigrades would probably survive. Then there are bacteria living miles beneath the Earth's surface, in solid rock, surviving on chemical energy with no sunlight whatsoever. These organisms represent a vast underground biosphere we barely understand. They are isolated from surface conditions, protected from all but the most extreme catastrophes. They are a backup copy of life, waiting in the depths. There are organisms living at the bottom of the ocean near volcanic vents, in water heated to hundreds of degrees under crushing pressure, in total darkness, sustained by chemicals from the Earth's interior. There are bacteria living in the ultra-salty Dead Sea, in acid mine drainage, in radioactive waste. Life has found a way into every possible niche on this planet. This diversity of survival strategies means that something will persist through almost any catastrophe. The asteroid that killed the dinosaurs? Plenty of survivors. The Great Dying? A few species pulled through. Even if humans cause a 6th extinction, many organisms will survive. They may not be the ones we care about. They may not be the charismatic megafauna, or the beautiful birds, or the colourful fish. But life will go on. And here is the beautiful part. Evolution does not mourn what is lost. It immediately begins working with what remains. The survivors become the founders of new lineages. Within a few million years, always a few million years, biodiversity recovers. New species fill empty niches, ecosystems stabilize, the planet heals. Humans exist because of an extinction event. We are here because an asteroid killed the dinosaurs and gave mammals their chance. That lineage led to primates, which led to hominids, which led to us. In a very real sense, we owe our existence to catastrophe. We are the children of disaster and survival. But here is what makes us different from every other species that has ever lived. We know this history. We can read the rocks and reconstruct what happened millions of years ago. We can see patterns. We can understand the mechanisms that drive extinction. And most importantly, we can use that knowledge to prevent the next one, at least the ones we have control over. We are the first species that can detect asteroids and deflect them. We are the first species that can monitor volcanoes and predict eruptions. We are the first species that can measure atmospheric carbon dioxide and understand its effects. We are the first species that can choose to protect other species from extinction. We are the first species with foresight. That foresight comes with responsibility. We know what we are doing to the planet. We know the consequences of habitat destruction, climate change, pollution, and overfishing. We cannot claim ignorance. The data is clear. The science is settled. The only question is whether we will act on what we know. Here is what gives me hope. Throughout history, humans have faced existential threats and overcome them. We have survived ice ages, droughts, floods, famines, and diseases. We have built civilizations in deserts, mountains, Arctic tundra, and tropical jungles. We have split the atom, walked on the moon, cured diseases, and connected the entire world through technology. When faced with problems, we innovate. When faced with challenges, we adapt. The current extinction crisis is a choice. Unlike past extinction events caused by asteroids and volcanoes, this one is driven by human activity, which means human activity can stop it. We have the technology. Solar and wind power can replace fossil fuels. Electric vehicles can replace gasoline cars. Sustainable agriculture can feed the world without destroying rainforests. Protected areas can allow ecosystems to recover. The solutions exist. What we need is will. We need to value nature not just as a resource to exploit, but as the life support system it truly is. We need to recognize that human prosperity and ecological health are not opposed. They are interconnected. A healthy planet supports human civilization. A damaged planet puts everything at risk. Young people around the world are demanding action. They see the crisis clearly because it will affect their future. They are not burdened by decades of inaction and excuse-making. They simply see the problem and demand solutions. This gives me tremendous hope. The generation coming of age now gets it. They understand we are running out of time, and time is the one resource we cannot create more of. Every year we delay action makes the problem harder. Every species that goes extinct is gone forever. Every degree of warming triggers more feedback loops. Every ton of carbon emitted adds to the problem. The time to act is now, not tomorrow, not next year, not when it becomes more convenient, now. But alongside the urgency, remember the resilience. Remember that life has survived 5 mass extinctions. Remember the tardigrades and the deep-sea bacteria and the organisms living in impossible conditions. Remember that after every catastrophe, life rebounds. This should not make us complacent, but it should give us hope. The planet will survive. The question is whether we will survive with it, and whether we will preserve the incredible biodiversity that makes Earth special. Look up at the night sky. See those stars? Some of them may have planets. Some of those planets may have life. But as far as we know, Earth is the only place in the universe with complex multicellular life, with forests and oceans and animals and ecosystems. We may be alone in the cosmos, a tiny island of complexity in a vast desert of emptiness. That makes Earth precious beyond measure. That makes every species irreplaceable. We are living in a unique moment in history. For the first time, a species has opened its eyes and looked at the universe comprehensively. We can see back to the Big Bang. We can see across billions of light years. We can understand the forces that shape galaxies and planets. We can read the history written in rocks. We can reconstruct mass extinctions that happened before anything remotely human existed. But with that knowledge comes a burden. We can no longer plead ignorance. We can no longer claim we did not know the consequences. We know. And knowing means we must choose. Inaction is a choice. Action is a choice. Both have consequences, but only one leads to a future where humanity and the natural world thrive together. The universe is dangerous. That's true. Asteroids orbit, stars explode, volcanoes erupt. But the universe is also awe-inspiring. It created stars from hydrogen. It created planets from dust. It created life from chemistry. And on this one small planet, that life became aware. It became capable of understanding its own history and shaping its own future. We are stardust that learned to think. We are the universe made conscious. We carry within us atoms forged in the hearts of dying stars. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was created in stellar furnaces and scattered across space by supernovas. We are literally made of star stuff, connected to the cosmos in the most fundamental way. For billions of years, life on Earth was passive. It could only react to whatever the universe threw at it. Asteroids hit and species died. Volcanoes erupted and species died. Climate changed and species died. Life had no say in the matter. It could only survive or perish based on chance. But we are different. For the first time in 4 billion years, life has opened its eyes and is watching back. We see the asteroid coming. We can deflect it. We see the climate changing. We can stabilize it. We see species going extinct. We can protect them. We are no longer passive victims of the universe. We are active participants in shaping the future of life on Earth. That is the most incredible realization. That is the message I want you to take from this journey through Earth's catastrophic past. Yes, the universe is dangerous. Yes, extinction events have happened before and will happen again. Yes, we face threats from space and from our own planet. But for the first time ever, we have the knowledge and technology to do something about it. The dinosaurs could not prevent their extinction. The trilobites could not save themselves. The species lost in the Great Dying had no choice in their fate. But we do. We can survive. We can ensure that future generations inherit a planet as beautiful and diverse as the one we were born into. We can become the first species to not only survive an extinction event, but to prevent one. The question is not whether we can do it. The question is whether we will. And that answer is being written right now by the choices we make today, by the actions we take tomorrow, by the commitment we show to protecting this fragile, precious, irreplaceable planet we call home. The universe is watching. History is watching. Future generations are watching. And the Earth itself, this ancient survivor of so many catastrophes, is waiting to see what we will choose. Choose wisely. Choose hope. Choose action. Choose life. Because in the end, that is what this story is about. Not death and extinction, but life and persistence. Not endings, but new beginnings. Not the disasters that happened, but the survivors that endured and the lessons they teach us. We are those survivors. We carry within us the legacy of every creature that ever lived and struggled and passed on its genes. We are the latest chapter in a story 4 billion years old. And we get to write the next chapter. Make it a good one. The end.